So I said you can start.
Okay, sir. A very warm good evening to all. Welcome to second day of SPARC online workshop on CO2 refrigeration systems, fundamentals, advancements, and application. Today's first section is Transcritical CO2 refrigeration system control, a practical approach by Mr. R.P. Kamath from Danfoss. Mr. R.P. Kamath is a graduate in electrical engineering from Kerala University in 1981. Mr. Kamath worked with Quick India Limited, Blue Star India Limited, and Danfoss in sales and technical support. He has experience in various types of industrial, commercial refrigeration projects and air conditioning systems. Mr. Kamath has good knowledge in different type compressors, controls, applications with different refrigerants. He also worked on Transcritical CO2 projects. Presently, he is working as a consultant on Transcritical CO2 and industrial refrigeration applications, including ammonia and subcritical CO2 system. I request Kamath sir to start his section.
Yeah. Thank you, Dr. Shiva. I will start sharing the screen. Let me know if my screen is visible.
Not yet. Not yet. You have to share the screen.
Okay.
Okay.
Okay. Yeah, I think I just did. Yeah.
Yes.
No, now it is
Yes,
there.
sir.
Yeah. Okay.
But top portion is also there.
Huh?
Sir, please change to that slide mode.
Slide mode.
Okay.
Yeah.
Yeah, the side box can I?
Yes, sir.
Okay.
Now it is perfect.
Okay. Yeah. Thanks for guiding. Yeah. Good evening, everybody. My role is today to talk on controlling of transcritical CO2 systems. It is a little bit more complicated, but considering wide audience, and I'm not very familiar with everybody, I'm going in a middle path. So I will try to highlight what are more critical for transcritical systems, and just touch upon things which are similar to subcritical systems. So by and large, these are the topics covered in the today's 1 hour. I will try to finish in 45 minutes, 50 minutes. Now, if you'll see, there is a slide number coming somewhere here. Now, my suggestion is that if there are questions, maybe you could note down the slide number and ask the question at the end of the session. So it's easy for me to respond to that.
But unfortunately, slide number is not visible for us. So
is it now it is showing as 2?
No,
here.
that is hidden by that bar. I don't know. It may be for everybody or only for me. I don't know. Okay.
You are right. It is hidden for me also. Anyway, I will keep saying the slide number as I remember. It is, you're right, it is getting hidden. I don't know how to change it now. So we'll go with the comparison of transcritical versus subcritical. Now, this is the pH diagram for CO2. Typical CO2, typical subcritical system. Critical point is here about 31 bar and 73 bar 31 degrees centigrade. So obviously it is a subcritical system. Like we have been working on such systems for I don't know, more than a century or so. So things are pretty much simple, mechanically controllable, and everybody knows what to do. Now, in controlling this, one thing is you need to control the evaporating pressure. The second is the condensing pressure. The lower the condensing pressure, for subcritical, better is the efficiency because compression ratio is less. But this is not the case when it comes to transcritical system. In transcritical system, there is no latent cooling or heating, which means we are gas cooling. There is no condensing. From in this example shown, 95 degrees to this is 95 degrees C. It is just sensible cooling. Now, since there is no saturated gas or pressure, this is not the optimal condition where it can work on, which I will come in the next slide. So we need to find which is the optimum point, which is not at the moment possible to be done mechanically, which we need electronic interference, electronic control. How it's, let's see. Now this is a 35 degrees C constant temperature line. So obviously this is 30, 25, 20, etc. Now you can see in this area, the temperature is, sorry, this curve is almost horizontal. Of course, not 100% horizontal, but almost horizontal. But after a typical point, it starts climbing. The slope is very high and the other curves follow the same. Now, this also gives us an advantage in controlling the pressure or getting better efficiency. How it is, let's see. Now, in this, I will show a typical condition for 35 degrees centigrade with 80 bar, 90 bar, 100 bar. Now, please keep watching here. This is the work done and this is the delta H for the NRE, net refrigeration effect. Now, let's increase to 90 bar. When we did 90 bar, proportionately so much has increased for the work done. COP went up from 1.72 to 2.51. Now you can see here from this much, the work done has increased only little bit, hardly any this. So definitely it is advantageous to go for a higher pressure. Now the 100 bar. Now at 100 bar, now the slope is starting to come down. See, this is the 100 bar curve. There is little bit increase in capacity, but almost similar increase in work done. So the optimal point is somewhere peaking here. Now, so in control point of view, for us, the important point is to find this optimal curve, which is like this. So if it is 40 degrees centigrade, you are somewhere like 104 bar, 37, you are at 100 bar, and so on, till it becomes subcritical. When it is subcritical, we try to maintain a constant subcooling. Now there is now we are aware that there is no optimal required. Optimal is lower condensing, but here we start maintaining a constant subcooling. I will go slightly fast. The earlier one was slide number 5. Okay, discharge pressure control. As I said, lower the discharge pressure, lesser power consumption. In gas cooler, it is an optimum condition we need to find out for each corresponding temperature, cooling temperature. Then intermediate control is not applicable in single stage system for a subcritical system, whereas for transcritical 2-stage or single stage, it is applicable. And we need to find a best performance point, and it requires electronic control. Now, ejector not applicable for subcritical. Fortunately, it's applicable. I mean, it is an option available to us to increase efficiency. Little bit more, I'll say in the next slides. Evaporator control, more or less, it is the same for, you call it subcritical or transcritical. In evaporator, it was a thermostatic, manual, or electronic. And evaporator now it was predominantly electronic. Now Danfoss has come up with a solution for thermostatic expansion valve as well to bring down the cost for the evaporator. Oil management for subcriticals is simple. Electronic, it is not so simple. It is must. I'm sorry, for transcritical, it is must. Electronic control is must, and it is complicated. Now let's look at the gas cooler control. Gas cooler pressure control, I mean to say. Now this is the optimal curve I was saying. Now how it is, the compressor is discharging. This is using a ejector. Now discharge pressure goes to the ejector. It leaves some suction gas and puts it into the intermediate pressure, whereupon so the mean to say there is a pressure difference between evaporating pressure and intermediate pressure. It can be 3 bar to 10 bar. So this we can have an option to have a parallel compressor to suck this gas coming from the intermediate receiver. So you have energy efficiency. So that free energy is coming from the ejector. And here it also requires a valve to maintain the pressure difference between intermediate pressure and the evaporating pressure. Now to do this, we tap this points, gas cooler inlet outlet pressure temperature and gas cooler outlet pressure. Sorry, this is inlet temperature. Gas cooler, that is the air temperature, air on to the gas cooler. It is not outlet, I'm sorry. Meaning based on the gas cooler inlet temperature, the controller will find out this curve, and the ejector or the control valve will maintain the required gas cooler pressure. As I said before, at lower temperatures, it maintains subcooling. This can be controlled within some parameters. Similarly, we cap it at 100 bar or so, where you can turn it left or right. I notice slide number is not visible. The earlier slide was 7. This is 8. Now, using ejector, this is the curve we will be trying to control. Now, working principle of ejector. Now, high pressure comes into this here into the nozzle, where the nozzle is becoming smaller and smaller. The pressure is lower, so therefore there is a possibility of sucking from this nozzle. Then, as it is going out, it is protruding. I mean, the diameter of the nozzle is increasing, which means the pressure is increasing, and that is going to the intermediate pressure. It's explained like this. So meaning inlet from here, suction come from the evaporator, and it goes to the intermediate pressure, from where it will be going through the gas bypass valve to the next compressor. Now, this is how a multi-ejector is working. This is slide number 11. Multi-ejector is a Danfoss product. It has 6 ejectors. So you can have 4 ejectors or 6 ejectors. Now in this example, the first 3 are off. The 4, 5, 6 are on. How the gas flows? High pressure inlet. Now this being off, these valves are closed. That also has an additional check valve to prevent backflow. And the gas goes through this downwards and sucks vapor. Now it goes up through these nozzles outside, and meaning from outside it goes in like the jacket. It goes inside and comes down, and it is delivered to the intermediate side. This is how we are managing the show. Then these are having different capacities. So as per the capacities, we are able to adjust the flow required through the ejector. Combination of it's a combination of 4 different models: 125 kg, 250 kg, 500 kg, and 1000 kg per hour. Meaning in bigger ones, you will have 2000s here, 500 here. Some combinations are possible. Now we have basically 4 ejectors. Now the largest ejectors will be always placed in the beginning, and the smaller one will be the last. The smallest will be the last. If one ejector doesn't give the required capacity, meaning the total capacity is more than say 3,000-4,000 kg per hour, then we can add a parallel block, one more ejector in parallel to increase capacity. Now, it's a little bit complicated. I'll try to make it understand. In ejectors, there is a possibility to have HP ejector, LP ejector, and liquid ejector. Now, HP ejector. In HP ejector, we can have a entrainment or suction pressure lift of 6 bar or 11 bar. Actually, it does 5 bar also. 11 bar is sort of kind of maximum. The higher pressure is based on discharge gas pressure. Just I will, when it comes to the next one, to make it clear, I will explain it. Medium temperature compressor, suction to the compressor, discharge through the gas cooler, ejector, medium suction vapor is also sucked through the ejector, and raised pressure, it goes into the intermediate pressure. Now from intermediate pressure, we suck into another compressor. This is called a parallel compressor. Now, if the pressure difference is 11 bar, just putting some dummy numbers, if we were running this compressor at 10 bar suction, this one is working at 21 bar suction. So this compressor is going to give us much more capacity. I mean, much more capacity, energy saving as compared to we did not have this. And that is coming because of it's added. Even you can do this without ejector, but because of ejector, it is further enhanced. Max available is 11 bar. Now, LP ejector, in LP ejector, there is no parallel compressor. Here, what happens is from the empty, you suck into the ejector and raise it to intermediate pressure receiver. Bypass valve is here. The difference is whether it is, I mean, whatever it is, this compressor is sucking elevated pressure only. It is not directly sucking from here. Sorry, it is sucking only the suction pressure. This gas bypass valve will reduce the pressure and give it here. No, I'm sorry, I completely confused. This non-return valve will prevent that. Sorry. This non-return valve will make the difference between the empty evaporator outlet and the suction. So this compressor sucks only at elevated pressure. Now the advantage here, okay, I'll get into that in the next slide. And the next one, last one is liquid ejector. Liquid means you run the empty evaporator with a very low superheat such that it runs almost flooded operation. Means you are not controlling superheat anymore. So that will leak out some liquid from the evaporator. Therefore, the efficiency of the evaporator is much more. And CO2, yesterday, Professor Pramod was saying, the efficiencies, theoretical efficiencies are very close to actual efficiencies. So with liquid in, the efficiency is even higher. But then you require an accumulator to separate the liquid and vapor. And that liquid, whatever is coming, will be sucked by the ejector. and put it back to the receiver, intermediate pressure receiver. HP ejector. I explained this parallel compressor. In terms of only parallel compression, that is, there is no ejector. That means only the gas bypass valve was there. If this was not there, then we would have got up to 9% efficiency if there was only parallel compression. Now, by introducing ejector and if there was no parallel compression, meaning with ejector and parallel compression, in efficiency is increased by 17% and saving of 15 to 35% swept volume for the bigger compressor. Cost of the system can be less on large systems, but smaller systems the cost cannot be less because ejector also costs a bomb. It's also like a so to say, not exactly, but similar to costing similar to a compressor. So in small systems, it may not be optimal to use. Currently, target capacities is 100 kW, 150 kW and above. In warm climate, parallel compressor is expected to take about 75% of the load. And in cold climate, this parallel compressor may not take any load because it's not required. It may run at subcritical also, and only this compressor will take care. LP ejector, here notice that there is no parallel compression. Energy data 15% lower than without ejector, 34% as compared to 404A. This can lift, ejector can lift the gas evaporators to the receiver. Required swept volume of compressor will be 75% of what a normal system would do, which means by doing this, basically, somehow the gas is diverted from here, and we are now using this compressor at a higher evaporating pressure, so higher suction pressure. That is giving the efficiency. Generally, first cost will be similar compared to using a parallel compressor or ejector. Liquid ejector. Again, I had the liquid is getting sucked like this. It can be added to any combination of the systems. Flooding is managed independently by another controller. Gas suction accumulator is required. Yep. And here it is expected to give up to 5 bar pressure lift. Same in LP ejector, it's expected to give 3 to 5 bar lift. Maybe sometimes 6, but as Danfoss we commit 5 bar. If the ejector cannot pump liquid, then it will run to high superheat mode and there will be no liquid coming. Ejector will not work in that form. Just giving an idea of the product range. I'm not trying to sell. Now here 4 models which are 4 ejectors and 6 ejectors. In liquid, 1 ejector and 2 ejector. And this is how it looks. The 6 ejector or 4 ejector, the body is same. Now, when you don't have an ejector, how do you control? You still need to follow the optimal curve. So this is achieved using this HP control valve. I have combined a lot of things into the same slide to save time. Now this valve is called CCMT. Primarily now I am explaining how we control the PGC gas cooler pressure using the controller using this CCMT. Now parallelly CCMT is also used or can also be used for gas bypass or as an expansion valve in the evaporator. We have this many models. Heat recovery. In this diagram, this is the compressor inlet and compressor outlet. And before gas cooler, you introduce two heat exchangers for hot water recovery, heat recovery. In this example, there are two hot waters shown. One is this one is used as tap water. Tap means in cold climates you need hot water for bathing or for even washing the hands at 55 degree. The other one, this one is used Europe generally they are using for floor heating or even outside the supermarket where the road is frozen. You circulate the water, hot water to keep it if not warm, melt the ice at least. That's why two are there. And we have these three-way valves. It's controlled by the external electronic controller. Now, these are supposed to work depending on the water heat requirement here, or if there is no requirement, allow the complete gas to go to the gas cooler or control in a modulating way so that cooling doesn't suffer. It gets it gives you the heating. Little bit about the valve. It can withstand 140 bar, controlled by the controller, bipolar magnet type motor. It is used one inlet, two outlets, or two inlets, one outlet. Either way, this is a common inlet. I don't get too much into this now. It is based on the requirement, customer's requirement. We can adapt it to the need. Now, this controller, what I'm showing is AKPC 782A. This is one of the systems, one of the ones which you use also for the ejector. Now, this controller will take care of controlling entire high side equipments and the intermediate pressure equipment, but it doesn't take care of the evaporator. Evaporator, you need another controller. At best, we can give some feeling of the evaporator into this, but the controller doesn't monitor the evaporator. It also has a small display, but invariably this while using, you need a laptop or a monitor and some software to monitor or set or things. And also requires skills. It's not complicated, but it's a dedicated Danfoss this thing. Now, one controller can control 8 empty or parallel compressors. That is 4+4 or only 8 empty compressors, or 7+1 or whatever combination, and 4 low temperature compressors, step and speed control, meaning it can be 2 compressors can be variable speed and it allows step that is piston compressors, unloading, loading, that is the step control. Then we are also able to provide an oil management algorithm in this. Gas cooler fan, if it is fan or pumps, we can have a step or speed control on the pumps or fans, up to 8 fans or 8 pumps from the controller. Certainly 8 pumps may not be required, but this is mainly has been designed for the fans, air-cooled version. Then intermediate pressure receiver control, heat recovery control, 2 valves which was mentioned before. And also there are some general purpose input outputs for handling pumps or external other things which may be required. There are 3 PI controllers pressure integrated controller inbuilt in the program, which we can use for some purposes. Then ejector function is included. There is USB or PC connectivity. Now, just one more thing. This one particular will have some digital inputs, analog inputs, digital output, and analog outputs. This is the parent main controller. We keep on adding more extension modules to it, depending on our requirement of analog inputs, analog outputs, digital input, digital output, stepper input, stepper output for controlling the CCMT or any variable controlled valve, etc. So accordingly, we can install this in parallel to it. If it doesn't fit in one line, we fit to the next line with another connection module. Like this, we can connect up to 15 modules. Of course, it depends on some limitation, but generally it is able to control good TCO2 system. Now, superheat control, it is similar to subcooling. Electronic expansion valve, you have a temperature transmitter, pressure transmitter, then you have a controller. It's just controlling the superheat. Means like a thermostatic. This one shown is electronic. We have two types electronic expansion valve, AKVH or CCMT. I will not get into details. This max pressure is 90 bar. This one is 140 bar. Recently, we have launched thermostatic expansion valve for this, which means you don't need electronic control for this. It will work like our normal. It has a bulb and external pressure equalizing, which is connected at the suction. So simple electronic, simple thermostatic expansion valve. This is a very recent launch. Oil management. What I'm showing is one with common oil separator. Now here, what are the components required? You require an oil sensor on the compressor to know whether it has an oil, what level it has, and high-low oil switch or sensor on the oil separator. Then oil solenoid valve. How it functions, upon low oil level in compressor, the solenoid valve will open and allow oil to pass into that compressor. Means individually, each compressor. The if there is a low oil level in oil separator, it will trigger an oil recovery cycle. I cannot explain it in this diagram, but then it brings back oil. Unfortunately, in TCO2 systems, oil gets collected in the receiver. So sometimes, depending on the complication of the system, it becomes necessary to run a recovery cycle to bring back oil to the oil separator or reservoir. So that's called oil recovery cycle. So that's how it protects the oil management. Now the same system you may have with an oil reservoir if the system is big. So you have a better collection of oil and better oil management. Two things I want to highlight here. One, we are connecting this oil reservoir to suction line. That is to bring down the pressure inside the oil reservoir to closer to suction pressure. Otherwise, what will happen is if you give this oil directly from discharge pressure, there will be foaming in the compressor because compressor crankcase is at suction pressure. So that is the this, and there is a check valve to prevent backflow. Yep. Some other controls, that is a solenoid valve type EVT, it can go up to 140 bar, 3 by 8 inch, only one size is available. This can be used for oil. There is one more type called EVUL. We have 3 models in that: quarter, 3, 3.5. Then ball valves up to 158 are available. We have 2 variations in this. GBCT is 140 bar. See, the difference is these ones you may be able to use at intermediate pressure level or suction, whereas 140 bar can be used on the high side. Check valve, we have up to 5.8, again 140 bar rated. Then pressure switch, this is the HP switch. This can also be used as an LP switch by reversing the connection. Then pressure transmitters and temperature transmitters. I am not having a track of time. All the same, I'm on one of my last slides. Gas, then there is also gas sensor called DGS. Now, oh, I am good in time. Okay. Okay, this is my last. I will show this video. This has been developed by Danfoss for showing two-phase flow, two-phase.
Voice is not coming.
Oh. Oh. Is it audible now?
No, sir. The audio is coming.
Huh?
No sound, only video.
Yes.
Oh. Oh. I have no idea how to handle that.
I think yesterday I gave this website to them. So that
Okay.
they can see themselves.
I think so. That will be better because I don't know. I'm new to Zoom.
You can show the website again correctly so that they can copy.
Yep.
People can copy this and play themselves from the YouTube.
Yep, that's right. Yep. Actually, if you select on Google Danfoss CO2 phase change video, it will appear by itself. Sorry, this is not URL. It is my file reference. So no need to copy this.
I know. So
You have
Google.
to.
Yeah, they can Google.
Yeah, they can Google.
Danfoss CO2 phase change, then it will come.
Yeah. Let me see if I can.
Yeah. You can directly pay it.
Yeah. Now on the top, this bar is not changing. I don't know how to remove it. Are you able to see the link? Yep.
Sir, that link is visible.
Yeah.
It is visible.
Yeah. Anyway, just Google for Danfoss phase change video CO2. You put some words, it will come. No problem. Otherwise, you can ask one of us, Professor Maya, me, or Professor Pramod Kumar. We'll share. Now, I can. Let's go back to the. Any questions or I'm sorry, I think I did it very fast. I had no idea about the time.
Participants who are having question, your hand so that we can unmute you.
Here are my contacts, just in case.
Hello, am I audible?
Yep.
Yeah. Sir, can we go to the slide number 7?
Yep.
Yes, sir. This diagram,
Yep.
actually, sir, from this line, one line is going to this ejector, that is gas bypass, and another one is going to the main compressor.
This is the gas bypass.
No, sir, above that line.
This one.
Yes.
This is the suction line going to the ejector.
Yes. And another part is going to this main compressor.
Yeah, no, I'll explain it this way. Please hold your question. Evaporator, this is the empty compressor sucking. Forget this compressor for now. Gas cooler, then the gas will go through this valve or ejector. We'll ignore this now. We'll go to the ejector and come to the intermediate receiver. Because of the pressure difference, ejector will lift some of the gas from empty suction, this evaporator suction, and dump it into intermediate pressure. Now, this will give a pressure lift of up to 11 bar, depending on the evaporating and gas cooler pressures. Now, once you are here, this at higher pressure, you don't have to put it to the empty compressor. I'll put a number. Let's say this is working at 38 bar. That's like a water chiller, 38, 39 bar. Now we can lift it to by 10 bar to 40 bar. Okay, it's an absurd example. Let's say 6 bar, you can lift it to 16 bar. So this compressor will run from 16 bar to 90 bar. This was running from 6 bar to 90 bar. Yeah, now please ask the question.
Yes, sir. The main thing is mass flow rate. Means some mass flow, some part of mass flow rate will be taken by this ejector as a suction flow, and some part will be taken by this empty compressor. So,
Yep.
sir, what factor decides this mass flow rate? Means because for a certain motive flow, there must be a fixed suction flow for this ejector, and for each compressor also there must be a suction flow. Because compressor is designed for something, some specific thing. So how this mass flow rate is divided into those two parts?
It's a very good question, but there is no simple answer. I will try to explain it this way. You are only seeing one compressor here. We can have up to 4 empty compressors and 4 IT compressors. That is parallel compressors, which can be also dissimilar sizes or same size, which means when you are running 4 compressors or 1 compressor, the capacity is different. All this is managed by the controller. Now, how you manage it? Gas cooler evaporating pressure is managed by itself. It has a controller, which I was explaining. So when cooling is required, it ensures independently what is the cooling required. Accordingly, it gives liquid and vapor is formed. Now, on the other side, we are trying to regulate the gas cooler pressure. How? Based on the cooling media temperature. Like if air temperature is 30 degrees centigrade, we try to maintain, and it will give some kind of, if you are having 30 bar economically sized gas cooler, you may have 35 degrees centigrade as the gas cooler temperature. Now, according to that, it will find what is the pressure required, maybe 90 bar or something like that, and it will try to maintain that. Accordingly, it varies the loading on the ejectors. What flow is going through that? It is coming from the controller. Then on the compressors, you also have speed control or step control. Now, this compressor is running based on evaporating pressure. This pressure, this pressure means it will try to deploy the least amount of compressors required to maintain this pressure. Now, this compressor that will be based on how much is required will be based on this pressure. So I'm not sure if I answered you properly, but it's a complicated, no single simple answer to it.
Means,
But I really
sir,
appreciate. Yep.
means, sir, the first mass flow priority will be going to this ejector. Ejector will take the motive as it will be calculated from this. Sorry, ejector will take the suction according to the motive, and rest will be going to this compressor. Something like that.
Rest is not correct. Because if the ejector is taking less, you will also have less of compressor running. See, we have put some numbers here. It is approximate. Let's say empty evaporator is 60%. If this is the mass flow coming, 100% is this 80 plus 20. Now gas cooler is getting 100%, ejector is getting 100%, but when it in this line you have 140%, meaning what you are sucking from here. And then again, as you are taking out 60%, you are giving 60% here, and 80% is going through this that way. So you are right that we give preference to ejector to control the ejector pressure, optimal ejector pressure. But rest flow doesn't go to evaporator. When your mass flow is less, this compressors deployed also will be less, running at less speed or less number of compressors will be running.
Okay, sir. Thank you very much.
Yep.
Sir,
I appreciate it's a really nice question.
Continuing the same slide, why do you need HP control valve? Is it?
It is an optional. You may or may not use it. In case ejector doesn't become operational, this will take over.
Sir, why we have this gas bypass here in this system?
Okay, good. I will have to refer to something else before. See, this is a simple system. You have compressor, the evaporator, accumulator. This is the HP valve. Okay. Now, how it goes is evaporator this way. Now you can see that it has some liquid and lot of vapor.
Yeah.
Because of this, it is we are not able to bring it to here. Now, so this is waste going into the evaporator. You are unnecessarily giving lot of waste gas into the evaporator. So we have a bypass introduced. Now these lines are very feeble, but please try to. This is the evaporating pressure. Then we bring it and find out an intermediate pressure. And bring it to intermediate pressure. Now what this means, see, for a typical condition, whatever is imagined here, 55% only liquid is going and 55% vapor is going. Whatever is evaporating, meaning what I showed here, that liquid which is giving actual vaporization, that only is going here. Rest is separated here in the, meaning rest of the vapor will be collected here and bypassed into the compressor. So you are actually, you can see there is no NRE is same, work done is same. So what is the big thing in bypass valve? We are bypassing unnecessary, I mean this gas which is not contributing anything. We are bypassing it and giving it to the compressor. Is it understood?
Yeah, right, sir. But how this receiver decide the quantity of bypass gas and how it's like distributed there, sir? Can you just tell?
No, that is the
Little?
electronic control.
Okay.
Okay, I'll explain it this way. Again, this valve will decide what is the pressure required by the gas cooler, optimum pressure for the gas cooler. Accordingly, this valve will change position 0% to 100%. Now, bypass, depending on a optimal or pre-decided intermediate pressure, this valve will be controlled again by the same controller.
So these two are in loop.
Yep. In loop means
Expansion valve.
both are expansion valve. Yep.
Okay.
Can I ask a small question, sir?
Yes, sir.
Okay.
Thank you.
My question is on oil reservoir.
Okay.
You are having the pressure balancing equalizing, no? Yeah.
Yeah, I'll come to the slide so it is
Okay.
easier to understand. Yeah.
Yeah, that one. So
Yeah.
now you are ready. You are giving the suction pressure itself to the oil reservoir. Then how the oil will flow back? You know, pressure higher level. The oil
Sir,
reservoir.
you really very nice question. Sir, this check valve is having a pressure drop. It is not giving exact. There will be a pressure differential between this and this. If this is not having, we will have to have a. Thank you for this question. We will need to have a control valve here to differentiate the pressure. Meaning, if the suction pressure is X, X plus something will be here, not the discharge pressure.
Okay. Slightly more pressure than the suction pressure.
Yeah, let's say 3-4 bar or 5 bar. Yeah.
So not the oil reservoir can be hydrostatic pressure is not sufficient to flow.
Hydrostatic means gravity.
Your gravity flow. Oil reservoir can be kept up at 1 meter up than the compressor. So the pressure is same, but the gravity will not make the flow.
Yeah, maybe it may be, but I have seen normally what happens is you have multiple compressors, so many components compared to a subcritical system. So, and you have a pressure to keep things compact. So you always don't have the luxury of having that height.
Okay.
So yeah, that could be a solution, but mostly people are doing with jugglery of this pressure.
Okay, good. Okay.
Yeah. Thank you, sir. It is a good question.
Thank you.
Yeah.
Time I will have a small clarification again.
Please.
If no other questions, I will proceed with my doubt. Gas cooler pressure to be optimized, and you have got the line. You optimize the pressure line there. Okay. So you take the gas cooler exit temperature or air coolant temperature and control the pressure. So that is pressure is controlled mainly by if the ejector is there, ejector opening, right? How many ejector will be opened?
Yep.
Right. So if the pressure is false, you will close the ejector.
Yep.
Right.
Exactly. If there is no ejector at all, then you are controlling with that throttling valve.
Yeah.
Okay. Good.
Or if there is no throttling valve, then possibly we are in subcritical situation.
That's good. Then one more small doubt.
Yep.
You have now developed a thermostatic expansion valve for carbon dioxide also.
Yep.
How it is different from the normal valve, or any special thing about it? If you can, share the things.
Yeah. The special thing is it can withstand higher pressure. Then this is almost same as what we are having. We have a TE2 in subcritical already. It is the same valve, same changeable orifice, and you need a connection to flare adapter to put this on. Bigger thing in this is it needs to withstand higher pressure. Then okay, not so big, but the gas inside this gas liquid mixture, this has to respond to CO2.
Okay.
Means, yeah, that is the difference here.
So it
Now-
will operate both subcritical and supercritical.
Yeah.
Both.
So,
So if my system is operating supercritical, it will
yeah.
operate, and same system will operate if it is ambient temperatures comes down to subcritical also it will operate.
Yeah.
Wow.
Actually, the thing is super or subcritical. One big difference in this is the
Always
pressure incoming to the expansion valve is intermediate pressure, not high pressure.
Okay. So you can't, let us say I got a very simple system. Okay, and my inlet to the then there is no separator, the intermediate pressure. I'm just feeding directly from the gas cooler. Not, that's not possible.
Then you may pass vapor also.
Yes. It may be supercritical. It is a high pressure gas.
I will not say it will not work, but it is not the way it is it would be recommended.
So for this you must have a intermediate pressure.
Yeah,
It
even
should
for
be,
electronic it will be the same. Means we will for an again for the evaporator efficiency also, it would be better to have the intermediate receiver.
yeah.
Yeah.
In conclusion, that the thermostatic expansion valve, what is it is the feed should be always liquid.
Sir, even for electronic,
It
it
should
is
be
preferable
100% liquid. It should be
even for
100%
electronic.
liquid. It should be 100% liquid. No gas bubbles.
Yeah, but that is so for both the type expansion valve. Even electronic, we require liquid. You cannot differentiate. But I think it may work, but normally nobody does this way.
Hello, sir. Can I ask a question?
Yep.
Actually, when I was using the school selector app for selecting this high pressure ejector, there are two types of ER, means intermittent ratio was showing. One is at dimensioning level and another is at operational level. So what is the difference between those two types of intermittent ratio?
I have to say I haven't understood that. Probably we can do this offline. I'm sorry, I haven't got you completely, but there is an answer. We can have that discussed separately. Means with cool selector. So you
Yes, sir.
can contact me on this. Your name is sorry, I
My
didn't
name
get.
is Prasenjit. I am a PhD scholar in Bitsville.
Okay. Yeah, please. We can discuss this offline.
What was the question?
In
Sir,
cool selector, how to while selecting the ejector, he's saying one way option is by dimension, another is something else, which I haven't understood.
Okay.
Yeah.
Okay.
Yeah.
Okay. Yeah. Thank you. Yeah. Thank you, Professor Mr. Kamath. Very nice lecture, and I think Vaishak will take over to thank you and introduce the next lecture.
Yeah. Thank you very
Vaishak.
much. Yeah.
Thank you, sir. Thank you for an excellent and informative lecture.
Yep.
So we move on to the next section, that is simultaneous milk chilling and pasteurization by Professor Madali Ramgopal from IIT Kharagpur. Professor Madali Ramgopal is a HAG Professor of Mechanical Engineering at IIT Kharagpur. After completing his MTech and PhD from IIT Madras, he has worked in EPL back at Bangalore. Currently, Professor is a Dean, Associate Dean, Faculty of Engineering and Architecture at IIT Kharagpur. He is also in charge of Institute Air Conditioning works for about 10 years. His research interests are refrigeration and air conditioning, conditioning carbon dioxide based natural circulation loops, solid absorption systems, and thermal comfort. He has delivered lectures on refrigeration and air conditioning NPTEL courses, which became one of the most sought after course in students' fraternity. So I request Professor Ramgopal sir to start this section.
Yeah, good evening, everyone. Can you hear me?
Yes, sir, you are audible. Your slide.
Yes, we can hear you. Yes.
Yeah. Thank you, Dr. Maheshwar. And I would, without wasting time, I'll share my screen.
Still not shared.
Just give me a second. I think I'm also not very familiar with.
Yeah, bottom there is
Yeah,
a
can you
share
see?
screen. Bottom there is a share screen is there. One bar
Yes,
is
sir.
there in the bottom. You have
One
got mute.
color button is there.
Is my screen visible?
Not
No,
yet.
sir.
The bottom there's a
Green color
bar
option is there.
wherein
Share
options
screen.
are given: participants, charts,
Yeah.
share screen in a green color or bluish green color.
Yeah,
Share
yeah.
screen is there.
So that's what I've. Yeah. That is what I have done. It is asking me to select window or the screen. So I'll be selecting the entire screen.
Window,
sir.
window you can see, then there
Window
is
or screen.
the option to you. Here, your
Yeah.
PPT is open already in your one of the table.
Yes, it is open.
Yes, sir. Now you can shift to PPT.
Is it visible now?
Yes.
It is visible. It is visible.
Done. You go to the full screen and probably the slideshow mode. Then it will be. Yeah, correct. Yes. Yeah, done. No, still you have to go for.
Yeah, once again, yeah.
You have to go for the full. Yeah, done.
Okay. So good evening, everybody, and I'll be discussing about one or two systems, CO2-based systems, which we have tried for simultaneous milk chilling and pasteurization. Just a brief introduction to the importance of dairy industry and the importance of having an energy efficient systems for milk pasteurization. Some statistics show that the global milk production is of course increasing from year to year. It was around 840 million tons in 2018-19, and it is 928 million tons in 2020 and 21. And interestingly, India is the highest contributor with almost 23 to 24% of the total global production. Typically, the dairy plants are characterized, the conventional dairy plants, they are characterized by high demand for energy because we require energy for heating, mainly for pasteurization, and we also require energy for cooling of milk. And electrical energy is, of course, also required for auxiliary equipment such as pumps, blowers, etc. And some studies show that due to high energy cost of existing method of pasteurization and chilling, dairy plants are facing problems of profitability due to high energy cost. So naturally, improving the energy efficiency is highly beneficial, especially to a country like ours, which is the largest producer of milk. So heat pumps can be used for both simultaneous cooling and heating. Instead of using a separate system for heating and separate system for cooling, one can think of using a heat pump where you are using both sides from the condenser as well as from the evaporator for heating as well as cooling. So they are theoretically they are pretty attractive, and in fact this is not a very new concept. It is very well known that if you can design a heat pump properly, you can use both heating and cooling outputs. But the problem is with conventional refrigerants, with most of the conventional refrigerants at least, meeting both heating and cooling requirements in terms of the temperatures and the quantity is a bit difficult. Because normally if you try to achieve the refrigeration temperatures, then you may not get sufficient heating or vice versa. So in this context, the CO2 based transcritical systems, they are very promising for both heating and cooling applications. So just a small brief on pasteurization. All of us know that the pasteurization is done basically to kill the bacteria and to increase its shelf life of milk. Pasteurization can be batch type or continuous type. Normally, the batch type is used for small capacity systems, whereas for large capacity dairy plants, we normally go for continuous systems. So pasteurization generally involves heating of milk to at least 63 degrees centigrade and holding it there for about 30 minutes, typically in a batch type pasteurizer, or heating to about 72 degrees and holding it at that temperature for about 15 seconds in a continuous type pasteurizing plant. And pasteurization is followed by rapid cooling of milk. We have to cool the milk to at least 4.4 degrees or less to prevent the growth of harmful microorganisms. So we can see that pasteurization requires on one side heating to at least 70 degrees or so, and again cooling to about 4.4 degrees. So if you look at the traditional dairy farms, traditionally they use either hot water or more commonly steam for heating of milk, and a separate refrigeration system for cooling. And generally for heating, steam boilers are used, and these boilers are typically driven by a variety of fuels like wood, coal, oil, biomass, etc. And in large dairy plants, ammonia is the most commonly used refrigerant for chilling of milk. Of course, there are some smaller plants which can also use synthetic refrigerants. So this is the current practice. Of course, pasteurization, you can also do it at different conditions. For example, if you look at this table, depending upon what is the temperature that you are maintaining, your holding times can be different. For example, what is called as a high temperature short time pasteurization, the temperature is 72 degrees and 15 seconds. You can also have high heat short time pasteurization where the temperature can be 89, 90, 94, etc. As you increase the temperature, the holding time keeps on reducing. Okay. And this is a typical schematic from ASHRAE handbook of a conventional pasteurization plant. You can see that you have the raw milk enters into this tank. From there it goes into a regenerator, and then you have a timing pump, and then it goes to a heater. This regenerator is some sort of an internal heat exchanger where there is an internal heat exchange between the hot milk and cold milk, and then from there it goes to the heater. In this heater, it gets heated up to the required temperature. Since we have to hold the milk at that temperature for certain time, a holding tube is used for holding the milk. And from there, depending upon the temperature, if the temperature is sufficient, then it goes to the regenerator. Otherwise, again, it goes back to the constant level tank. So this process continues till you get the required conditions. So this is a typical large-scale continuous type pasteurizer. Now, if you look at carbon dioxide, of course, I will not go through this. I am sure that this was discussed. What are the advantages, disadvantages of carbon dioxide, etc. So let me skip this. So coming to the transcritical cycles, I am sure transcritical cycles are also discussed in the previous listings. All of you, I am sure you are familiar with this. So why carbon dioxide is attractive for simultaneous cooling and heating? Why not other refrigerants? For example, if you consider, let us say, a heat sink temperature of about 35 degrees or so. So that means I'm maintaining a heat rejection temperature of about 35 degrees. So if I'm using ammonia, okay, and this is the 35 degrees, so this is the subcritical cycle. So you can see that if I'm assuming an isentropic compression process and the saturated suction condition, you can see that the discharge temperature is about 75 degrees. So 75 degrees is good enough for pasteurization, but the amount of heat that is available from 75 to about 35 or so is very low. Okay, maybe 10% or less. So if you are thinking of using an ammonia system for both simultaneous heating and cooling, you may have sufficient amount of refrigeration, but you are getting very little amount of heating at the required temperature. So if you go for example, some other refrigerant like R290, you can see that here the situation is even worse. That means the discharge temperature is much less compared to ammonia. You are getting hardly 40-degree discharge temperature, so you cannot heat milk with this kind of temperatures. One alternative is to increase the condensing temperature, even though the heat sink temperature is low. But that is, as you know, is not good for the overall system performance. So you can say that both these systems, either ammonia or R290, they are good for cooling, but they are not good for simultaneous cooling and heating because of the temperatures available at the heating stage. So when you look at the carbon dioxide cycle, since the carbon dioxide cycle that we are operating in transcritical mode, so the exit temperature of the gas cooler is independent of the pressure. So I can vary the pressure and I can achieve very high discharge temperatures and a large temperature drop across the gas cooler. So for example, here in this figure, you can see that. So I'm keeping the exit temperature at 35 degrees, but by increasing the pressure, so you can see that the exit discharge temperature is varying from 75 degree, 100 degree, 120 degree, etc. So you can get a large amount of high temperature heat. This is possible with the transcritical cycle because your temperature and pressure are not related, unlike subcritical cycle. So this is the major advantage of carbon dioxide cycle. Even though the cooling COP is less, since we are thinking of using both heating and cooling COP, if you look at the combined output, this looks pretty attractive. You can also see this one in temperature entropy diagram. You can see that there is a large temperature glide starting from about 100 degree to about 35 degrees. So you can see at least 50% of this can be used for pasteurization. So if the milk is entering at about 50 degrees or so, it can be easily heated to about 72 degrees, right? Again, as you know, for carbon dioxide systems, unlike subcritical cycles, one can optimize the discharge pressure so as to maximize your COP. And as Mr. Kamath has explained, there are different control systems are available for optimizing the discharge pressure depending upon the gas cooler exit temperature. So I'm not going into this. I'm sure you know the theory why there is a optimum pressure. And from the beginning, people have been interested in finding out the optimum discharge pressure for different gas cooler exit conditions, etc. So you can see that this is one of the classical paper by Bullard, where you can see how the COP is varying with different gas cooler exit temperatures and how there is an optimum pressure. And another important thing you can see is unlike the conventional subcritical cycles, because of the transcritical operation and very low critical temperature, the losses in expansion device are extremely high. For example, in this figure, the compressor loss, the blue color line is the throttling loss. The throttling loss is very, very high if I'm using a normal throttle valve. So from the beginning, there have been efforts to reduce this throttling loss, and ejector is one of the simple solutions for reducing the throttling losses. Of course, for larger systems, etc., one can also think of an expander. You can recover the work. So in this presentation, I'm just going to present some theoretical work and some few experimental results on some simple systems which we have tried for a pasteurization application, that means simultaneous cooling and heating application. Before I show the system that we have studied, I'll quickly show the conventional system. This is a conventional system which we call as CRC. Just an expansion valve and a single compressor. That's the simplest possible system. And this, as all of you know, is the ejector system where the expansion valve is replaced with an ejector. And we have a separator, phase separator for separating the liquid and vapor, and there is a feedback to maintain the mass balance across the separators. So this is again a simple ejector-based system. So in a simple ejector-based system, the expression for COP has to consider the entrainment ratio, because the mass flow rate to the evaporator is not same as the mass flow rate to the compressor. So the entrainment ratio is given by mu here. And this is a typical PS diagram of the conventional CRC cycle as well as your ejector cycle. Based on the thermodynamic simulations of the ejector cycle, I have not shown this one. One has an option of using an intermediate heat exchanger in this system. This is what we normally call as a liquid to suction heat exchanger. So we have tried the performance using the internal heat exchanger and without the internal heat exchanger, and then the system is optimized, and some correlations are generated for optimum conditions. For example, optimum pressure lift, optimum pressure lift at optimum conditions, what is the optimum gas cooler pressure, and at this optimum gas cooler pressure, what is the ejector efficiency, and how is it related to different temperatures, etc. So coming back to this is a general carbon dioxide based transcritical systems. Now if you come back to the systems for simultaneous cooling and heating of milk. So this is a typical milk flow in a dairy plant. Normally the raw milk which is at around 4 degrees or so is first clarified, then it is homogenized, then it is pasteurized as I told you at around 72 degrees in a continuous process, then it is chilled to 4 degrees. Then it is packaged and then it is stored. This is a typical schematic where you have a boiler for heating the milk to 72 degrees, and there is a intermediate heat exchanger, sometimes called as the regenerative heat exchanger. This is a very, very important component. What we are doing here is instead of heating the milk from 4 degrees to 72 degrees and again cooling it from 72 to 4, we are using this heat exchanger for recovering heat from the hot pasteurized milk and transferring it back to the cold milk. Okay, so this is that is the role of this. So this is a conventional system. So as I told you, we require a separate refrigeration system for chilling and a boiler for heating. Now the system that we have considered for simultaneous cooling and heating of milk, there are several possibilities are there. For example, we call this system as RCEP1. Again, you can see that this system uses an ejector in place of an expansion valve. Then you have a phase separator, and this is the expansion of from the suction pressure to the evaporator pressure. And you can see that there are two gas coolers because the required temperature, the temperature glide in the gas cooler is from about 35 degrees to about 100 degrees or so. So this entire temperature range is not useful for milk heating. So only a part of the gas cooler heat can be used for heating of milk. So remaining has to be rejected to the surroundings. So it is split into two parts. In gas cooler 2, we are rejecting the heat to the surroundings, or maybe for some low temperature heating, etc. But the milk is essentially pasteurized in gas cooler 1. So in this scheme, the internal heat exchanger is used between gas cooler 1 and 2. So if you see the refrigerant flow from the gas cooler 2, it enters into the ejector, and then this is the primary or motive fluid, and then the secondary fluid from the evaporator is entering at 10. They're getting mixed and they're coming out of the ejector at 7. And then you are separating out the liquid and vapor. Vapor goes back to the intermediate heat exchanger, and then it goes to the compressor, from the compressor to gas cooler 1 and intermediate heat exchanger and gas cooler 2. Okay, and if you look at the milk side, the milk is entering at TMI. It is passing through the regenerative or intermediate the heat exchanger. And then from here it goes to gas cooler 1, getting heated to 72 degrees. And again, it is transferring heat in this heat exchanger. And finally, it is passing through the evaporator and coming out at about 4 degrees. So this is one possibility. The other possibility is the intermediate heat exchanger. Instead of keeping it in between gas cooler 2 and 1, you can also keep it after gas cooler 2. So then this you call it as RCEP2. Rest of the circuit is same, so only the gas cooler position is shifted. Now this is without intermediate heat exchanger, because we really don't know whether intermediate heat exchanger is good or not, especially for when you are using an ejector. So we have to assess the performance and see whether it is really required or not. So we have, this system is studied without any intermediate heat exchanger. Otherwise, it is same as RCEP1. And finally, this is a conventional system with an expansion valve, but with intermediate heat exchanger between the gas cooler 1 and 2. So there may be several possibilities are there. And you can see that we have considered only a single stage system with a single compressor. Okay, a very basic system. These systems are conceived based on the experimental setup that is available in our lab. So we did not go for more complicated systems for analysis. So these are the 4 cycles which we have analyzed for simultaneous cooling and heating of milk applications. And if you consider the first cycle, that is RCEP1, this is the typical TS diagram. This is with the ejector, so you can see that there are 3 pressure levels: the evaporator pressure, and the suction pressure, and the gas cooler pressure, and the different heating. So essentially the milk is getting heated from 2M to 2, and the intermediate heat exchanger is 3M to 2, and the low temperature gas cooler is from 3 to 3M. Okay, and at 3 it is entering into the ejector. Okay, and this is the pressure lift is P8 minus P9. And we have defined these performance parameters. For example, one important parameter is what is called the specific milk flow rate. That means what is the milk flow rate per kilowatt of compressor power input. So you can see that this is m dot m is the total milk flow rate divided by the compressor power input. So in terms of the state properties and the entrainment ratio, you can show that this is equal to this parameter. And then we have defined what is called as the pasteurization performance coefficient, or COP pasteurization. COP pasteurization, this system is producing a useful refrigeration effect, and it's also producing useful heating effect. But the entire heat is not available for pasteurization. Only part of it is available for pasteurization. So the pasteurization COP, we have considered only that part of heat which we are using it. We assume that the remaining heat is rejected to the surroundings, which is not useful. So based on that one, we have defined this COP. And then we have compared this with a conventional system just to know what is the energy savings. So the percentage saving of energy is given by this expression. So in this expression, you can see this NGC and NGH are for the conventional system. What is the energy consumption, or we assume that we are using natural gas as a primary energy. So what is the natural gas consumption for the cooling system, and what is the natural gas consumption for the heating? Okay, and this NGP is the natural gas consumption for the transcritical CO2 system. So the difference gives you what is the energy savings. And just for the sake of comparison, we have considered these values. We assume that we are using R22. This is a slightly old study, so we assume that R22 is the refrigerant used, and with a COP of about 5. And we are using a boiler with an efficiency of about 70%. And we can assume that the power generation efficiency, that means power generation from natural gas to electrical power or mechanical power, is about 32%. Okay, and this is the calorific value of natural gas. I'm not going to show all the results, but some typical results are shown here. For example, for the first system, that is RCP1, you can see in this graph what we have plotted. Here, as I told you, the intermediate heat exchanger, or the HXD, is a very important component, and we are also going to invest money on that one. So we need to really find out what sort of effectiveness that we need to have for this heat exchanger. So in this graph, you can see we are varying. So we are varying the effectiveness of the 3 heat exchangers. One is the gas cooler one, that is this red line, and the other one is the intermediate heat exchanger effectiveness, and this one is your regenerative heat exchanger effectiveness, right? So 3 heat exchangers we have considered, and we are varying the effectiveness of each of these. And while varying the effectiveness of one heat exchanger, we have kept the effectiveness of the other heat exchangers constant. For example, when I am varying the effectiveness of this HXD, this is the milk heat exchanger, from 0.6 to 0.85, we kept the effectiveness of other heat exchangers at about 0.85, that means 85%. Okay, just to see the individual effects. So you can see from this graph that naturally, as the effectiveness increases, your specific milk flow rate increases. That means per each kilowatt of power, the amount of milk that we can handle increases. But out of all these 3 heat exchangers, you can see that the milk heat exchanger has the highest effect. Okay, so that means this has the most dominant effect on the specific milk flow rate, and the intermediate heat exchanger has the least effect. So even though I'm varying the intermediate heat exchanger effectiveness from about 60% to 85%, the improvement in specific milk flow rate is not that much. Whereas if I'm varying the milk heat exchanger effectiveness, the improvement is almost 100%. Okay, so this tells us where to invest. Okay, so we have to have a good milk heat exchangers, followed by the gas cooler one, and least importance to the intermediate heat exchanger. Again, you can see that what is the effect of your gas cooler pressure. This graph, please look at it a little carefully, because from this graph, we'll decide what sort of effectiveness is required for the intermediate heat exchanger. So and what is the advantage of operating the gas cooler at higher pressure. And these three curves refer to three different gas cooler exit temperatures. So the exit temperature is varied from 35 to 41 degrees. So for a given gas cooler exit temperature, you can see that as you are increasing the gas cooler pressure, the required effectiveness of intermediate heat exchanger goes on decreasing. That means you have to have an efficient intermediate heat exchanger when you are operating when your gas cooler pressure is low. But if you are operating on a higher side, then you don't require a very effective. So you can your cost, initial cost can be reduced. Okay, and you can also see that as the gas cooler exit temperature is increasing, the required effectiveness of intermediate heat exchanger reduces. So this gives us a decision on how much to invest on each of these heat exchangers, especially on the intermediate heat exchanger. Again, I mentioned about the pasteurization COP, what kind of values that you get for pasteurization COP. You can see that at a given gas cooler exit temperature, there is an optimum gas cooler pressure at which this pasteurization COP is maximum. Okay, and naturally, this maximum COP increases as your gas cooler exit temperature reduces. Okay, and you can see that the typical at optimum conditions, you get about 4.2 to 4.3. COP of 4.2 to 4.3. In this study, we have maintained the evaporator temperature constant at about 2 degrees centigrade. Okay. And this is the typical pressure lift that we can get across the ejector. For the three different gas cooler exit temperatures. Interestingly, as the exit temperature is high, you get a higher pressure lift. So the high exit temperature is at least beneficial in terms of the pressure lift, even though it may not be beneficial in overall system performance. So what you can observe is, depending upon the gas cooler pressure, you can get a theoretical, at least a theoretical pressure lift of around 7 to 10 bar. Okay, using the ejector. And this figure shows the work or heat transfer rates across different components. And you can see that the maximum amount of heat transfer is taking place across the milk heat exchanger. This is where most of the heat transfer is taking place, because remember that here we are cooling the milk which is entering at 72 degrees to maybe about 10 degrees or so. And simultaneously we are heating the milk from 4 degrees to about 60 degrees or 65 degrees. So most of the heat transfer takes place in this intermediate, the milk heat exchanger. Okay. And in other components, the heat transfer is less. And obviously in the intermediate heat exchanger, the heat transfer is much less. Okay. And these are the typical results at an optimized condition. For example, at a gas cooler exit temperature of 38 degrees. So the optimum gas cooler pressure is about 145 bar. And we require 85% milk heat exchanger effectiveness, and the gas cooler 1 effectiveness of 85%. And the intermediate heat exchanger effectiveness need not be more than 40%. Okay, because you can see that the amount of heat transfer is also less. And under these conditions, your specific milk flow rate is about 0.5 kg per second per kilowatt, and your pasteurization COP is about 4.28. And if your refrigerant flow rate is about 1 kg per second, then in a day you can process about 1,75,000 liters of milk. So that means this can be used for a fairly big sized dairy plant. And I've told you that we have compared different systems. And this graph shows the comparison between different systems. So you can see that from this graph, the best performance is with RCEP1, where the intermediate heat exchanger is kept between gas cooler 1 and 2. That means you first use a gas cooler for heating of milk. Then refrigerant goes through the intermediate heat exchanger, and then it goes to the gas cooler one. So that gives the best performance. And interestingly, the second best performance is the system without ejector. Okay, that means these two systems, even though they use ejector, the position of the gas cooler is such that the advantage that you gain by the ejector is lost because of the position of the intermediate heat exchanger. So that means the conventional system without ejector but with intermediate heat exchanger in between the gas coolers shows much better performance compared to these two systems. So this means that one has to carefully identify the location and the size, etc., of the intermediate heat exchanger if one has to get the best performance. Obviously, the best place, the best configuration with the ejector gives much better performance compared to the conventional system with throttle valve. Again, if you compare the primary energy savings compared to the conventional system, by conventional system, I'm sure you understand. That means you are using a natural gas based boiler for heating of milk and a conventional R22 based refrigeration system for chilling of milk. So if you compare that, take that as the reference, then you can see that the energy savings with the transcritical CO2 system without ejector it can be about 20% or so, and with ejector it can go up to around 30%. Okay, so you can get a 30% energy savings. This is substantial energy savings. Of course, the initial cost of the transcritical CO2 system may be higher than the combined cost of your boiler and R22 system, but considering the significant savings, so the payback period may not be very high. And based on this simulation, we have developed some correlations for fixing the optimized conditions based on your gas cooler exit temperature, etc. So if somebody wants to design these systems, these correlations can be used. This model is a simple model, but the ejector is modeled properly so that we hope that it gives reasonably accurate results, maybe with within 10-15% of the actual systems. So these correlations may be useful for the initial design or selection of these systems for this application. We have also done some experimental studies. In fact, we have built this system way back in 2003 or 2004. Maybe this is one of the first transcritical CO2 systems in our country. So this is a very simple system, and it is completely in-house. I mean, we have built all the heat exchangers, etc., in-house, except for the compressor. All other components are made locally. So in this experimental setup, we tried the different types of expansion valves. For example, we had an ejector, we had an expansion valve. I did not show it here, but we also used a capillary tube. So just to study the effect of different types of expansion devices, normal expansion valve, ejector, and the capillary tube. So this system, we did not just use it for pasteurization, but we used water for the simultaneous cooling and heating of water. So the gas cooler and evaporator are tube-in-tube type heat exchangers. So evaporator produces chilled water and the gas cooler produces hot water. So you can say that it is almost mimics a dairy plant where the milk is getting heated in the gas cooler and it's getting chilled in the evaporator. We did not really use due to financial constraints, etc., any complicated controls. So the simple controls and the expansion valve manual. It's a manual expansion valve. Some small safety devices are used, and this is the experimental test rig. This is a very old test rig. We had a lot of problems operating this one because many of the things we did not understand when we have built it, but gradually we have understood the problems. So you can see, for example, there is a capillary tube here, and then there is a ejector here. Okay. And there is a manual expansion valve, and this is your evaporator. I'm sorry, this is your 2 is the gas cooler, and the evaporator is here, and these are the loads. So load for evaporator and load for the gas cooler, and some controllers are used for controlling the compressor. So this is again this ejector is designed and manufactured. Again, this may look little crude, but you can see that there are different components. They are all assembled as a stainless steel body. Okay, the different parts, and you can see that this is the primary nozzle, and this is the tip of the primary nozzle, and this is the body. Okay, and this is your So this is connected to the evaporator, and this is connected to the gas cooler. Okay, and this goes to the, this is from the diffuser, it goes to the phase separator. We also seen what will happen if I'm going for different tips. So we have designed it in such a way that this tip can be replaced, and we can also vary the mixing length. As I'm sure all of you know that in a typical ejector, we have a mixing section, and there is a constant area section, etc. So we can actually move this primary nozzle to and fro by using this arrangement. And we wanted to see what is the effect of that on the performance of the system, and what is the effect of the shape of these things on the performance. Okay, this is the work by one of our research scholars. Sorry. So as I told you, different combinations are used, different nozzles are, primary nozzles are used, and different mixing sections are used, and these are all the geometric details of these things. I'm not, we have seen that there is performance different depending upon these things. This, but if you are able to move this to and fro, that means this portion, the primary nozzle, if you can move it to and fro, you can get some control over the system performance. I'm just showing you only one or two results. This is a typical performance, the cooling and heating system performance as a function of your gas cooler inlet pressure. So here the evaporator is operated at 0 degrees centigrade, and this gas cooler exit temperature is 35 degrees. So you can see how the COP is varying. Okay, we could get a combined COP of about 4.5 at an optimum gas cooler inlet pressure of about 95 bar. Again, you can see the effect of gas cooler exit temperature. Again, the COP is varying widely. It is varying from about 2 to about 5. Okay, depending upon the gas cooler pressure and the exit temperature. These results are with a conventional system with the throttle valve. Then the same system is also studied without throttle valve and with an ejector. So for example, this is the result obtained from an ejector based system. So for one particular combination, as I told you, we had several combinations of the mixing lengths and the primary nozzles, etc. Okay, the typical results from one of the combinations. So we can see that if you compare this with the previous slide, we could get a noticeable improvement in system performance when the ejector replaces the throttle valve. And you can see the typical entrainment ratios, about 30% to 40%. And the ejector efficiency is not very high, but what we have seen, we got efficiency of about 10 to 15%. And what we have seen is that at least in those days, whatever data was available, the best, I mean, somebody can correct me if I'm wrong, but the result that we have at least come across is the ejector efficiency of about 20% or so. We could get about maximum efficiency of about 15%. And we could get, I have not shown the pressure lift, we could get a pressure lift of about 7 bar, or so a maximum pressure lift of about 7 bar using our system. So based on this particular study where we have compared the system performance for passive simultaneous cooling and heating of milk with and without ejector, we have seen that the ejector quite naturally and as expected, the system with ejector performs better than the conventional system under all conditions. And very important observation is that the intermediate heat exchanger is not always beneficial. So one has to really assess depending upon the operating condition and whether we are using ejector or not, whether it is really required or not. If it is required, and where to keep it, and what should be the, what can be the its effectiveness. Okay. And as far as the ejector is concerned, I mean, you have to remember that this study was done many years ago, and now I'm sure the knowledge about ejectors, etc., is very high, and they're all commercialized now. So I think they're much better ejectors with a lot of information is available. But based on the initial studies done by us, these are some of the observations that we made. We have seen that the overall system performance is very sensitive to the throat area. So this we have observed both from the theoretical simulations as well as from experiments. And then exit area of the primary nozzle and the inlet area of the diffuser. And the CO2 system we have seen, if you are using it for pasteurization and chilling, you can get a primary energy savings of about 29 to 30%. And this I've already told you. So if you are thinking of using an intermediate heat exchanger, the position has to be decided carefully. Okay, and the ejector mixing length plays an important role. So again, this one has to properly assess depending upon the specific system. One has to design this carefully. Now there are a lot of theoretical models are there, and people are also using computational fluid dynamic tools for designing the ejectors. There are different types of models. The model that we have used for design of ejector is based on the homogeneous mixer, but we have considered the compressibility effects, etc. But we assume that the two-phase mixer is a homogeneous mixer. And our results are not too, I mean, when we compared the theoretical ejector performance with the experimental ejector performance, the difference is not too much, maybe about 25 to 30% or so. So we thought this model is not very bad. So these are the studies based on the transcritical, conventional transcritical CO2 system with or without ejector and with or without intermediate heat exchanger. Okay. We have also done some theoretical work. I mean, we are, frankly speaking, I am not very sure whether it has any economic viability or not, but it is conceptually, it is somewhat interesting. So this is a solar-assisted trigeneration system for cooling and heating of milk. So in this system, we are using high temperature solar collector through which the carbon dioxide flows. This high temperature carbon dioxide is used for generating power in a turbine, and a part of the power is fed to the compressor, and remaining part is available for other uses. So that means we are getting electrical power out of this system, and we are using this system again for chilling of milk and also pasteurization. So that is why we call this as a trigeneration. That means we are producing refrigeration, heating, as well as power. So if you see the working principle, do I have another 5 minutes time? Can I take another 5 minutes time?
Yes, sir.
Okay.
Yes, sir.
So if you consider the refrigerant side from the evaporator, the refrigerant is entering into the compressor. It is getting compressed from 1 to 2. Then it passes through a recovery heat exchanger. In a recovery heat exchanger, this carbon dioxide which is coming from the compressor gets sensibly heated by extracting heat from the refrigerant which is coming from the turbine. So this recovery heat exchanger is an internal heat exchanger where the hot carbon dioxide coming from the turbine rejects heat to the relatively cool refrigerant coming from the compressor. Okay. So, and at condition 3, and at high pressure, it enters into this concentrated solar collector where the carbon dioxide gets heated up to really high temperature, maybe 500 degrees or so. And at this condition, it passes through the turbine and it produces power. And after that, the pressure which is equal to the gas cooler pressure, it goes through the recovery heat exchanger where you are recovering some heat. Then it goes to the pasteurization heat exchanger where it is used for heating the milk. And then finally it goes to the gas cooler where the remaining heat is rejected to the surroundings, and from there it goes to the throttle valve. Okay, and then evaporator. So milk is entering, and just like the previous system, milk is sensibly heated in the milk heat exchanger by extracting heat from the pasteurized milk, and then from there it goes to the heating user heat exchanger, or what was called as a gas cooler 1 in the previous system, and then from there it goes to the milk heat exchanger, and finally it goes to the evaporator. And this is the temperature entropy diagram. There are 3 pressures here. One is the pressure, the intermediate pressure, the gas cooler pressure, and the turbine inlet pressure is at 4, turbine exit pressure is 5, which is same as the gas cooler pressure. Okay, and then you have the evaporator pressure. Okay. So of course, one can also think of replacing this throttle valve with an ejector. So that this system is exactly same as the previous system. The only difference is that here we have used an ejector in place of a throttle valve, and the rest of the components are same. Okay, so because we are using ejector, the TS diagram gets modified, and you can see the modified TS diagram here. So on this system, quite naturally, we could not do any experiments. We didn't have neither money nor the components. So, but we have done some somewhat detailed theoretical studies and detailed simulations. And here we have again defined the performance parameters, just like overall COP. So here, even though we are getting power output, we still prefer to use the term COP. So here the COP consists of, in the numerator, 3 outputs. One is the power that we are getting from the turbine, the excess power that we are getting from the turbine, and then the heat that we are using for pasteurization of milk, and then finally the refrigeration capacity for chilling of milk. And the only input is the input in the solar collector. Okay. So you can see that in this, we did not, of course, there are some studies where carbon dioxide is not directly passes through the solar collector. Use some other oil or something in a concentrated collector and generate high temperature heat, and then use that heat for heating CO2. But in our system, we have directly allowed the CO2 to pass through the solar collector, because in recent years, there were some studies where in fact people have developed concentrating solar collectors where carbon dioxide, supercritical carbon dioxide is used as the fluid. So there are already some studies. So that is the reason why we did not consider any intermediate fluid. Okay, so the collector itself, the collector fluid is carbon dioxide. So there is only one working fluid here. Okay, just to give you, there are many trigeneration systems. For example, combination of Brayton cycle and absorption cycle, Brayton cycle and compression cycle, etc., using different working fluids. Okay, and with these trigeneration systems, people have generated heating, cooling, and power. But in our trigeneration system, there is only one working fluid. It uses only carbon dioxide. Okay, so there is no other system. So we felt that this is a much simpler system compared to the conventional trigeneration systems, which are actually hybrid systems and a combination of different types of systems. So we defined the COP in this manner. Then we also defined, just like the previous study, the specific net power output. Okay, specific net power output for particular for this system is for each kilowatt of solar, how much electricity that you are generating, or how much mechanical power that you are generating. That is given by the specific net power output. Finally, we have also defined the specific milk flow rate. That means for each kilowatt of solar heat, how many kgs per second of milk can be handled. Okay, the milk flow rate per kilowatt of solar. Okay, these are very preliminary thermodynamic analysis results. So you can see what happens as you are increasing the medium pressure. Medium pressure means the gas cooler pressure. So as you are increasing the gas cooler pressure for different gas cooler exit temperatures, what sort of COP that you get. Here the COP may appear to be very low, but you have to understand that the denominator is solar heat. It is not electrical power or anything. So quite naturally, you don't expect very high COP here. Okay. But still you can see that you can get a, depending upon the conditions, you can get a COP of about 1.5 or so. Again, you can see what is the effect of the cycle high pressure. Interestingly, you can see that the high pressure is much higher than what we normally use in a transcritical cycle, because you have to generate power in the turbine. So the high side pressure is 200 bar, 220 bar, etc. But you can see that as you are increasing the high side pressure, your COP is actually decreasing. Okay, and for different turbine inlet temperatures, as I told you that turbine inlet temperatures are pretty high. So that means one has to really go for a concentrating type collector, okay, to generate this kind of power, or maybe if you have some other source also, you can think of using that. So importantly, this is the electrical power that you can generate, the specific net power output. So we can see that you can generate about 150 watts of electricity per 100 watts of solar heat input, which is not negligible. Okay, so remember that rest of the power is going into the compressor. Okay, so the turbine is producing much more power and the remaining is going into the compressor. So this is the power available for other auxiliary equipment, lighting, etc., or for driving the pumps, fans, and all. Okay, and the specific milk flow rate. Here the specific milk flow rate is much less compared to the earlier system, because in the earlier system that is based on the denominator is electrical power, whereas here the denominator is solar heat. Okay. So again, at a typical optimized conditions, we just show a comparison what sort of values that you can think of. Okay, so this is based on 1 kg per second of total refrigerant flow rate to the compressor. So you can see that you can generate about 93 kilowatts of turbine power. Out of that, 75 kilowatt goes into the compressor, right? And the balance is available as mechanical or electrical power. And the evaporator cooling capacity is about 125 kilowatt. And we are recovering about 125 kilowatts of heat for pasteurization. And the milk flow rate is about 3.13 kg per second. Okay. And the solar heat available is about, solar heat required is around 187 kilowatt. We've also done solar field calculations, and this is again based on a PhD thesis of another research scholar. So he has designed the solar collectors and he has designed the solar field. Okay, so using the standard LS2 type parabolic trough collectors, we have seen that you require about 8 to 9 standard collectors. Standard collectors are not designed for carbon dioxide. So what we have done is the tube we have redesigned so that it can withstand the high pressure. Otherwise, the other parameters remain more or less same as the standard collectors. Okay. So this is some fundamental studies that we have done on CO2 based systems for simultaneous cooling and milking. We have also done some studies for simultaneous cooling and heating of milk using other systems like compression absorption systems, etc. long back. But what we find is out of all the systems that we have considered, the CO2 based systems definitely are very attractive because of the large temperature glide that we are getting using a single compressor. Okay, so just to conclude, based on all these studies, we can improve the primary energy efficiency by about 30%. So it looks certainly very promising. Again, somebody may correct me if I am wrong. What I feel is for small capacity systems of hundreds of kilowatt or so, ejectors are definitely preferred in place of throttle valve. But if you are looking for really very large capacity systems, maybe one can think of an expander in place of an ejector for much better efficiency. And the second system for remote locations where if you have solar heat or high temperature waste heat like waste heat from biomass, etc., then one can really look at the trigeneration system, which in my opinion theoretically is interesting, but requires a lot of feasibility studies and development of components, etc. Otherwise, it looks quite attractive. The major problem for us means for our country is the development of critical components. So as I told you, the experimental system that we have developed, we had to import the compressor from Dorin, and we also had to import the electronic expansion valve. We have used an electronic expansion valve in a subsequent study that is also imported from Italy. Rest of the heat exchangers we could manufacture locally. Okay, but they are pretty expensive because they are not mass produced. So if you really want to make them economically viable, we have to develop industries locally so that we can produce them on a mass scale. I mean, I don't see any reason why the systems cannot be economically viable once you have all these components available locally. Of course, anybody who is not really familiar with these systems gets scared when he looks at the operating pressures. But from our experience, we have been working in this for almost last 20 years. We have done a lot of experimental studies. We have built systems also. If you take care of the safety aspects during design and during operation, these systems are, I mean, we have never had, thank God, any accidents. So one can take care of these things, but one has to be really careful at the time of design and operation. Of course, there is a major need for creating awareness about these systems. Now, it's so nice to see that big industries, giants are producing these, and the components are available now. One can build these systems by buying these components. And it is also important to disseminate the knowledge, and proper training also is required if you want to make these systems popular. One very important thing is, I'll just in our curriculum, we have to really introduce these transcritical systems, because traditionally most of the textbooks, that whatever we have seen, the very popular textbooks, they don't discuss about these things. But I think when we teach refrigeration or other energy systems, we should discuss these systems. This is my personal opinion. With this, I conclude. Thank you so much. If you have any questions, I am most welcome. Hope I have not exceeded my time.
Thank you, sir. Participants who are having questions, please raise your hand so we can unmute it.
Achha, by the way, how do I come out of the share this thing?
Sir, on top there be one.
Yeah. Okay. Right. Yeah.
Can I ask a question?
Yes, sir.
Okay. Professor Ramgopal, is a wonderful lecture. I enjoyed it. I got a basic question. In the liquid internal heat exchanger between GC1 and GC2. Hello?
Yes, sir. Yes, sir.
Okay. What is the exit temperature of CO2 entering the compressor?
Exit temperature of CO2 entering the?
Yeah, no, exit. What is the temperature of the CO2 which is entering the compressor after your internal heat exchanger?
Yeah, that, I mean, I don't remember the values, but you can see that the effectiveness is about 40%.
No,
so it is entering at 2 degrees. 40%, sir. 40% is the effectiveness. So we can calculate it is entering, the vapor is entering at 2 degrees. And on the other side, if you consider after the milk, so the CO2 is entering into this intermediate heat exchanger maybe at about 60 degrees or so. Okay, so about 58 degrees is the delta T maximum. So if you consider 60 degree as the delta T maximum and 40% is the effectiveness, that means 24 degree is the temperature rise. So that means it is coming out at about 25 degrees or so. That means it is entering into the compressor at about 25 degrees.
My contention is why this heat exchanger should be put in between. Why not after the second gas cooler? You can attain the same temperature by increasing the heat exchanger effectiveness. That will give you additional cooling because you are entering the ejector at lower temperature. So I will
Sir, I mean, as I told you, we have tried that option also, but for this particular system, because one of the combinations is where we have kept the intermediate heat exchanger after the gas cooler, like what you have suggested, right? But when you are considering the overall performance of heating and cooling, we find that what you are saying, maybe it is good if you are considering only cooling, but if you are considering both cooling and heating, we find that keeping it in between these two gas coolers, that gives the best performance.
See, for heating, it depends upon what is the inlet temperature of the gas entering the compressor. By increasing the heat engine effectiveness to 60 or 70 or 80%, same temperature can be obtained, 26 degrees centigrade can be obtained, even if you are putting internal heat exchanger after the second gas cooler. No? Okay.
Yes, sir.
Okay, so by having
one small this thing. Remember that we are also using an ejector. So with ejector, the intermediate heat exchanger is not always beneficial with ejector. Because what is going into the ejector is a low enthalpy fluid.
But I agree. But this, what is the efficiency of the ejector you have assumed?
Efficiency, I mean, as I have shown you,
if it is 20%, then heat IHX will be useful. If it is more than 30-40%, IHX may not be useful.
That those studies also we have, sir. Due to lack of time, I did not present that result. We actually have those things. We have identified like a map under what conditions one should use IHX and under what conditions IHX should not be used, depending upon your ejector efficiency, etc. We have those results.
Okay.
I mean, I can share those results with you. Okay, so that is what in one of the conclusions we said IHX has to be really selected based on the other components and other operating conditions. So for certain conditions, it is beneficial and it is required. But for certain other conditions, it is not required. And it also depends, as you very rightly said, on the ejector efficiency.
Okay, thank you.
But I don't have the I mean, frankly speaking, this is my research scholar's work. So I don't remember all the numbers and all.
Same question of IHX in the tri-generation system. Why you are not using IHX in the tri-generation system?
IHX in the tri-generation system.
Yeah, you're not used. Is it not worth? Especially when there is no ejector.
That is true, sir. Of course, we did not. I mean, we have to use it and check what happens. But my personal opinion is, I mean, CO2 we have seen there are studies which recommend IHX, and there are many studies which don't recommend IHX. And I personally feel that adding another component, and so we want to have a minimum number of components.
Okay, good.
So, but this is something we need to study for the tri-generation system, whether IHX is really beneficial or not. We have not studied.
Okay. Okay. Thank you very much. Thank you.
Thank you, sir.
If there is no other questions, I request moderator Vaishak to thank Professor Ramgopal for the wonderful lecture, informative lecture, and carry forward. Dr. Vaishak.
Sir, there are few more questions actually from participant side. Dinesh, you had a hand. Dinesh, you can unmute from your side.
Yes, sir.
Please ask your question.
Yes, sir.
Yeah, please. Yeah, Dinesh,
Sir,
you want to...
Yes, sir. Yes, sir.
You want to ask any question or no?
No, sir.
No, okay. I think one more person is there. Okay, so if there is no further question, we will move on to next presentation. And before that, I thank Ramgopal sir for this wonderful lecture. So next presentation is latest development in INDEE Plus demo set.
Thank you so much.
This is presented by Dr. Simarpreet Singh from NTNU. Dr. Simarpreet Singh is currently working as a scientific researcher at NTNU, Norway, in an ongoing Indo-Norwegian project, Future Refrigeration India, INDEE Plus, supported by Ministry of Foreign Affairs, Norway. Dr. Singh had completed his postdoctorate in collaboration with NTNU, Norway, and Indian Institute of Technology, Madras, under the framework of INDEE Phase 1. Dr. Singh also contributed to an eminent project, IF, Center for an Energy Efficient and Competitive Industry for Future, funded by Research Council of Norway and industrial partners. The work was focused on to improve the overall performance of a dairy industry. Dr. Singh's strength is inclined towards advancing eco-friendly heating and cooling solutions, R744 technology for various applications. Having more than 5 years of research experience, his work focused to attract potential vendors, manufacturers, and industrial technocrats to promote R744 technology as a prominent solution to enhance the overall performance during subcritical and transcritical operations. Moreover, Dr. Singh believes that the research work could potentially achieve its capability once it grows along with the industrial collaboration. I request Simar sir to start his presentation.
Yeah, Dr. Vaishak, can you hear me?
Yes, sir, you are audible.
Okay, perfect. Let me share my screen with you.
Sir, your screen is visible. Yes, PPT is visible now. You can start.
Okay. Thank you for inviting me for this workshop, and I would like to acknowledge Professor MP Maya from IIT Madras to consider me as a part of this SPARC project. And today I would like to mention about the progress, the recent progress which we are producing in Indian scenario, in Indian HVAC sector, by making it possible to have our live applications in on ground and for various areas and sectors. So let me start with so my what I'm going to discuss is the latest development in INDEE Plus demo site. So INDEE Plus, which I will be discussing later on in detail, is the recent ongoing project which is in collaboration with the NTNU Norway and other academic institutes in India as well as in Norway. And funding is given by the Research Council of Norway. So we'll discussing it. And I'm Dr. Simarpreet Singh, working as a scientific researcher in NTNU Norway. And previously I was working in IIT Madras and in collaboration with NTNU in the same project, but the phase one. So the contents which I am going to discuss in today's lecture is we'll talk about something about the introduction, about some background about why, what is the risk, some importance of CO2, about the project INDEE Plus, what is the project, why this is important to be discussed, and why everyone in India who belongs to this HVAC sector needs to know what we are progressing. The educational unit, as mentioned by Professor Ramgopal, that this technology needs to be discussed. The people needs to be trained and educated. So I'll discuss about the educational units which we are developing, and there is one which is already in the practical part. Our 3 to 4 demo sites, which will be available after 2 years for everyone to be part of that, to see how these things are working in practical, how the CO2 is performing in real world, and what are the outcomes of this project, some expected outcomes and some on the ground already, and the acknowledgements about it. So let's start with the introductory part. So I would always say that don't call it change, call it climate emergency. As you have seen, there are many problems which are growing. And yes, we have addressed a few, but there are still many. And this is not because of only the industry and the other chemicals, but it's also because of the lifestyle which we are adopting, and we are liking it very much. But there is always a solution for the lifestyle and for the processes or for the culture which we are adopting. So what we are growing here with this project and with this initiative and with this idea is we are going towards the green revolution, or I would overemphasize it as a clean revolution, not the green only. So there are many things and many practical aspects and applications which could be addressed with the eco-friendly solution. There are many applications such as automobile, fishing, marine, CO, industrial, process industries, domestic application, hotels, chillers. So there are many applications which could be easily addressed with CO2. And later on, we are going to discuss this as how the system should be and how effectively this could work for such type of application. But this is a possibility that we could see the change in the future with this technology. As we have already discussing yesterday, Professor MP Maya has already discussed that there is a new element, and which is now coming in the picture, in which we, with the help of which we are evaluating the actual performance of the system and units. It's not only GWP, it's not only ODP, but the TEVI, the overall contribution of TEVI in the unit. So this is a small example of how this TEVI is actually acting in a real world. So whenever a system is designed and it is running, only the direct emission we are talking about or we bother about, it's just the 20%. But in the background of this system, which is the indirect emission, is 80%, which is actually a huge number, which is a part of concern. So that is why this TEVI, total equivalent warming impact, is coming into the picture, which is considering both direct as well as indirect parameters to evaluate a system, not only GWP, not only ODP. Why I'm saying this? Because nowadays in the market, you may have observed there are many upcoming refrigerants which are selling at the name of low GWP and green green refrigerants or green energy solutions, but they are not at all considering the total equivalent warming impact. What would be the overall reaction of this refrigerant once it will be in the ambient conditions? So just to clearly explain this one, you have seen the global warming potential of very traditional R12, R23, R11. So this the lower one is just the um, yes. So these are the just the comparison of how this R717 and R7444 is actually the benchmark for GWP for the various refrigerants which were used traditionally and still in India, I would say, are still using and applicable. But how this has to be changed. You might have seen this changing cycle. You have seen people were working with natural earlier, natural refrigerants, and then something has introduced known as CFC. Then suddenly the chemical industry and other technocrats have identified there is some problem with CFCs, with ozone depletion or other stuff. So then they have introduced a new phase of the refrigerants like HCFCs. So then again they have discovered there is some problem with the depletion and other process. Then the same industry which is providing you the solution is also giving you the problems. And then they introduce HFCs, but no one is now talking about what is the problem with HFCs, and then now they have introduced HFOs. But there is a study which is conducted in a Japan military base in which they have conducted an experiment with HFC typically, in which they have seen it is 20,000 times or maybe more than that dangerous than a acetic is acetic acid actually. So they are not talking about what is the overall impact of this on the ambient condition, but they are just talking about what is the global warming potential of this refrigerant. But still, these HFCs, when they will be introduced as a part of phase out, then only they will say, yes, it was harmful. So why to wait for another family of refrigerants to again create some problem or trouble in the upcoming system? We already have the solution. So it's not emphasizing the CO2 for this part, but this is the only solution we have in the industry now. So once we will understand that, we will try to make it applicable, we will try to make it cheap, we will try to adopt it as possible as. So it's not a single unit which is you could see in India, but there are many, many upcoming and already existing units around the globe. And the major part which is shared by the Europe now, they're much more aware, and definitely you could see a system which is already running in India, which is for some application area. But we are expecting many, many numbers in the upcoming years, maybe next 2 years, that India will also compete around the globe. And North America and South America is already working on that field, and Japan already said it. So they have already made this system as a, you could say, a benchmark or a normal solution, which they already preferring. So this is the scenario around the world. Why CO2? Just a small, we already maybe know these things. High operating pressure, heat transfer property of CO2 are very good. It is safe, comes under A1 category. It is the benchmark that, so saying GWP is 1. It is not at all covered in FGAS regulation, so there will be no protocol which will cover this CO2 or could ban this gas as a refrigerant. There's no taxation, energy efficiency in the moderate climates, and there are many applications in which one heat reclaim is the most effective one, which we could say. System could work for medium temperature, low temperature, heat recovery, and air conditioning. So the number of applications which are popular around the globe could be easily covered with this technology. It has low total equivalent warming impact, so the saving is energy cost is very high, and it is a potential application. And also there are many injectors and other applications which are already available in the market. While considering the fundamental properties, it is a bit different than the other traditional refrigerant which we normally discuss. So the part is the critical point, which is very low, and uh, this is also an opportunity for this refrigerant that this could work maybe much more effectively in supercritical or in, I would say, transcritical conditions. The operating pressure is definitely high, and as mentioned by Professor Ramgopal, if designed properly and used critically, this could be one of the game changer we could have. And there are some other properties. So this is a normal, a simple definition how this is different from a normal refrigerant or a vapor compression system. As you could see, this is the liquid vapor dome. So this is the critical point. So this, if our ambient temperature conditions are more than 31 degrees C, which is very normal in Indian operating conditions, the system works from subcritical, which is below this dome, to supercritical. So this operation is known as transcritical zone and transcritical operation. So once you will keep on increasing your ambient conditions, the operating pressure from A to B will keep on increasing. But this is also a beneficial part that this much heat could be used for simultaneous heating and cooling applications. So this is also a beautiful part of this technology. And the traditional system looks like the same for this CO2 as well. There are four major components: compressor, gas cooler, evaporator, and receiver and expansion wall. And one IHX is just an add-on addition to save the compressor and to increase the efficiency of the unit. So this is the difference between the simple and the transcritical system. Some typical example, if you want to use the heat reclaim, which we have discussed of this part, that if the operation is at higher ambient temperature conditions, what could be used this heat for? So just for making an example, and this is a live application working in Norway. So what they have done is they have distributed our condenser, or I would say gas cooler, in three separate portions, and they are using it for different applications. First application they are using for hot water. So they are making hot water and they are consuming it for domestic purpose. Then they are producing hot air, and then they which they are using further in their residential houses, complex, or some other part. And after that, then there is a third application which they are using for melting snow. So this is not the application which could be like could be faced this way or that way, but the amount of heat which is required. So the amount of heat and the temperature level which is required for the hot water temperature, it is fixed. So then the heat, rest of the heat which they do not want to waste, they have used it for the ventilation purpose. Then there's another part of heat which they really do not want to waste, they have used for the snow melting. So this is the heat reclaim, how they are. So typically they consider this as a heat pump system, not the refrigeration system, but the heat pump system. So the major part of these systems are focused on generating heat. But in our conditions, in our ambient conditions, we do not need to melt snow. We do not need to create hot air for our conditions. But definitely, there are some applications which we could identify, and such type of systems could be designed, which we are going to discuss. So there is a possibility of the CO2 in which you could use it for a number of different applications. So we were talking about the training. So how we need to design such type of systems, how to create awareness. So for that, I was part of INDEE phase 1. So in that part, IIT Madras and NTNU together designed a unit which is known as uh, refrigeration, as well as cooling and heating unit, in which we are generating heat as well as air conditioning, a medium temperature, a low temperature. So four applications you could consider here. So low temperature was, which we tested, was below -30. Medium temperature tested was below -18, and air conditioning we tested at 6 to 11 degree C, and heat reclaim we have identified, we have tested for 70 degree. So water we have generated up to 70 degrees C. So this part of the unit is available for the as a training site. We have conducted many workshops, many trainings. We have also designed a CO2 course for new generation and who are interested in uh, getting to know about this technology in India or maybe from abroad. So we are mostly targeting on the HVAC sector, not emphasizing, but we want them to see how this unit, how the system is, the complexity of the system could be handled, how this high pressure of the system could be handled, how the system could work efficiently, even for 5 parallel applications, and could be handled with a single unit. Traditionally, how we are using air conditioning, we have a split air conditioning in our houses. For water heating, we have electric geysers. For medium temperature, we have cabinets. For low temperature, we have another freezers. But this system, the beauty of this system is you could handle all these 5 applications in a single unit with a single system. So I believe the complexity is much, much lower as compared to handling 5 units with the one. And now the phase two, in the phase two, is planning to have 3 more training sites in India. One would be one which is selected as a BITS Pilani, another is ISC Bangalore, and the third one is CFT Kochi. And all 3 units which will be designed, the initial parts of the educational training site unit is already in the institute, already imported, and they are now institutes are working on designing the demo sites at which students, technocrats, industrial people, academic front people, they could come, get training, get to know the system, and discuss. And if they want to make their own system in their institute, these institutes could be a first uh, milestone for them to have reference for. So this is one of the objective of this Indie Plus, to have number of training sites in India in the future. And we have conducted many. So these are some glimpses from the students or the trainings which we have conducted as a classroom. So this is the system which you could observe here. So we have conducted many hands-on experience um, trainings with the unit. Students have seen how the system is actually working, with some basic knowledge before going on hand. So these type of trainings or these type of work could be keep on carrying on with this unit which we already have. Something about this unit, why I'm discussing it a lot, that you could easily observe the system already have all the major components which are now a part of the HVAC system in the advanced module. We have ejectors, low pressure ejection ratio ejectors. Then we have liquid ejectors. The system is it has 3 different cooling applications: air conditioning, medium temperature evaporator, LT evaporator, and on the other side it has heat reclaim, and the heat which we are not extracting from the system, it is taken care by the air cooled gas cooler. And as this is a test rig and demo site, the secondary loop is water glycol tank solution. And this is a fully optimized unit, and anyone could have a look and anyone could get trained on system. We have expert PhD scholars and PDF scholars who are taking care of this now. So if anyone is interested, they are very much welcome. And there is also an option to explore the possibility of having parallel ejector, which is not very much familiar nowadays in the study, but definitely there is a possibility to handle 2 parallel ejectors in the unit, and extraction could be easily identified. And you might have already seen how these ejectors are designed from the internal side, but now to just to have a better capacity handling, the Danfoss is offering cartridges, number of cartridges. In this, you could see 6 different cartridges in a single ejector, which is capable of handling varying load and different type of capacities of the unit. So this is one which you will easily observe in the unit, which is available in IIT Madras. It has solenoid valves, which is able to open and close the suction and discharge port of the unit. There are check valves which are operated because of the change in pressure. You might have already seen the basic principle how the ejectors are working. This is not different than that, but only this could handle a lot much capacity and variation in the capacity of the unit, as it will not stable. It will not stay stable during the operation, but it will keep on changing and varying once you will have it in the application area. So there is also another possibility that you could flood the evaporator. I believe this is not very familiar term with as compared to the traditional one, but now definitely there is a possibility to flood the evaporator to see what is the option. So this is the non-flooding condition. In the traditional systems, we have seen we are getting some superheated at the exit of the evaporator, but with the flooding, we are trying to fill the complete coils of the evaporator with fluid, in which so the heat transfer could be enhanced, the capacity could be enhanced, and this is the small example of non-flooding and flooding condition. So this is the condition, flooding condition. So this is the exit of the evaporator. So you could see a lot of liquid at the exit, and so this is the non-flooding condition. So this is the traditional with no liquid at the exit, very minimum vapors you could hardly observe. So this is the difference, and this could be tested in IIT Madras unit, and you could observe the capacity changing. You could see how the flooding could enhance the overall performance of the unit. So let's talk about what is Project INDEE Plus. It is under collaboration with Indian and Norwegian government. So there are many institutes are involved in this project, which is funded by Norwegian Ministry. You could see NTNU Norway, Center of the R&D, which is associated with the NTNU, Norwegian Environment Agency, which is required to create the protocols that CO2 needs to be in the major framework as compared to the other refrigerant. IIR is our distribution and marketing lead team, which is promoting this on the global scenario. ISC Bangalore, IIT Madras, BITS Pilani, CIFT, and CEW. So this is the CEW is from the Indian side to make the protocols and documentation and other stuff. So these are the all institutes which are now involved in this project to make it possible to promote this technology, as everyone is hoping that this could be a game changer for Indian HVAC sector. So as INDEE project is not a lone project, it is associated with other projects. SPARC is one of its parts, so in which we are now conducting this workshop. Akshay Patra is another project, and there is an Agile pool in which we are creating the study tours, and we are conducting many workshops and creating some courses for the upcoming generation for this technology. So major objective of this INDEE Plus is to create regulation. The first part is how this CO2 is creating emission from end to end of life of this system. So what could be the policy requirement, what should be the business model, and what should be the infrastructure which is required for this technology to become as a mainframe in a mainframe. So development and support of the units. So future refrigerant recovery, how we could recover the refrigerant, how we could recycle these systems, how could reclamation of the system, and disposable action of India. So for every technology, for every new refrigerant, these has to be adopted in a new manner. So for CO2, we are going to develop and support all these actions. Then there will be a frontier technology in which we are going to implement the future R&D project. We will identify, develop, and support the different vendors, manufacturers, and whoever is interested in making, maybe in the academic section. There will be many training facilities which you might have already seen, which are upcoming already. And there will be many demonstration sites. So we have mentioned 3, but we are hoping to have more than 5 after 2 years. So we are going to identify, develop, support, commission, and monitor the different applications such as supermarket, CO2 heat pump, chillers in hotels, CO2 refrigeration system, and fishing vessels. So we are going to discuss what is the progress of these demo sites in India now. So it is not only about the industrial side which is engaged in the project, but also the acknowledgement dissemination part, which is one of the major element in this project, in which we are going to advertise all the things. We are going to design CO2 courses in which we have initiated already. There will be a number of workshop and training programs in different parts of India with support of different events and other sites. There will be a project sites in which we will be going to discuss and disseminate all the results, all the outcomes, how to handle the unit, how to design it critically. As this will be separate design and will be critical for Indian ambient condition. As you have seen, we have a huge glide of -2 to 50 degree now. So this is a bigger challenge for us. However, in the European market or in the European scenario, this temperature glide is not this much. But for Indian, it would be a challenge, and that is also an appreciating thing to design such type of unit to handle these many. So there we are going to advertise it through different articles which are going to publish in local magazine and Indian journals. You might have already seen a few of that already. And there will be some industrial engagement in parallel, in which we are going to encourage different local vendors who could potentially assemble the unit, some technical staff which could be skilled, which could be trained and get the skill, uh, and the components which could be, as Professor Ramgopal said, heat exchangers and some of that components which are not very much critical to design could be easily manufactured in India. Only a few parts which are not right now available in India need to be imported. So this is the major framework of the project. The two things, industrial front and academic front, will work in parallel. So talking about the first demo site which we have decided, we are going to target the supermarkets. As you have seen, these are the major contributors of air conditioning requirement and medium temperature requirement and low temperature requirement. As you have seen the frozen products, you have seen milk and dairy products keeping in the supermarkets, and you have seen the air conditioned area in which people are walking and roaming and purchasing and buying, and there are some material which are laying uh, systematically in on the ground. So we are in talking with Metro Cash and Carry Bangalore main headquarters, which they are planning to have a new branch in Bangalore. So we are going to design their HVAC unit, and this is our timeline which we are targeting. And this is one of the major market in the future in India, in which the system is booming. And then there is a second demo site, which are hotels. As you have seen, hotels has different requirement. They need hot water as well as air conditioning. Hot water for different application. One could be washing area for laundry. Second is for cooking purpose. So these are the major contributors which are for the hot water. And third one is the air conditioning, which they need in the room, in the reception area, in the lobby. So the hotel is the second application which we have shortlisted. And now we are progressing with two demo sites in India. One is in Chennai and another one is in Goa, which we are proposing a unit which will be handling heating as well as cooling. And we are targeting that we will be having these both demo sites in 2024 for training and other purpose. And the third one, the important part, is the marine sector. As you might have seen, we are bigger producer in seafood, but due to the uh, you could say preserving it we failed somehow. So CO2 technology is introduced in a way that the quality of the cash could be increased to improve the overall profit in the global market. So we are already sending this cash to the European market, but once you will have such technology which will be in corporation with the existing one, the quality of the overall product could be increased, and might be possible in the future people will only focus on the one which is eco-friendly in the side, because Europe is already focusing on this now. So what is the development sector? How we are focusing the development of the demo sites in India? So we have a section written three different equal parts. One is the planning, second one is the development part, and third one is the implementation. So in the planning side, we have selected the applications. We have studied the geographical challenges. Where is the situation? What is the temperature glide? What would be the average temperature? The vendor locally, or maybe who would be interested, who would be a potential game changer for that demo site, and how the documentation would work. So how the collaboration would work, how the, because NTNU and other Indian institute will be the part of the training and knowledge dissemination side, but the main owner of the demo site would be the person who is going to install it in their premises. So vendor would be in direct contact, or manufacturer would be in direct contact with the end user. So in this case, end user would be the owner of the supermarket, owner of the hotel, or owner of the hospital, something. So this is the planning side. So the development side of the thing is the specification. What would be the application? Do they need heating? Do they have heating demand? Do they have cooling demand? What would be the peak load demand during peak load hours? How the oil management works? If the system is going to have different application, the complexity would increase, and how the oil management system would work. Next part would be the design, how the system would look like. And you have already seen Mr. Kamath has discussed many different configurations, and this needs to be studied while discussing about what is the need of the hour, how the parameters would be vary, what is the actual requirement, how much glide you need in the water, how much glide, or what should be the ambient condition inside the hotel or somewhere. So these are the parameters which need to be decided in the development part. And what would be the strategy? Strategy means how these needs to be contributed in a single perspective. So this is the development part. And then the implementation, how this system is going to have the control strategy, how we are going to get the maximum efficiency or the maximum output in the unit, how the system design, once it will be in the live part, will look like. What would be the specification of that unit? Means not, you don't have only the HVAC part, but also there will be a section which is contributing for the distribution, known as ducting. There will be a part which is uh, piping section. There will be another part. So that is come under the design part. During the implementation, you need to have a machine room in which you have to fix the controls and other part, or if you have a container inbuilt with the inbuilt system, how it's need to be implemented in the hotel, or such type of needs to be designed. And then what would be the documentation? Documentation means the results. What would be the outcome? How you are going to disseminate the results? What is the performance of the unit? So these are the part of the documentation. So this is how we are planning for each demo site. So let's talk about our first demo site, which are in the development phase in Akshay Patra Kitchen. Some of you may have already known about this organization, but I would like to tell you about something about this. This is a non-profit organization which is uh, supplying midday meal to underprivileged children in government or government-aided schools. Basically, they are countering the malnutrition and supporting the right to education. A student should not be stay away from the education just because he is hungry. So this is the main target which they are aiming at. So what is their current situation is they have 50 centralized kitchen in different parts of India, and They are providing food to every school, over 1.8 million children they are feeding in more than 16,000 schools in 12 different states across India. So their work is huge, their aim is huge, their motivation is huge. So as a, as a good initiative which they are taking, we are putting our part and we are designing a unit for these people in which we are going to provide hot water as well as cold water for these. And before that, we have done some energy, economic, and environmental studies in which we have evaluated what would be the profit or what would be the enhancement in the overall efficiency once you will have this unit, in spite of using their steam cookers or electric heaters and air conditioner, split air conditioning. So this is what we have come up with. Energy cost will be reduced in the cooling side by 55%, in the heating side by 27%, and in total 30% would be the saving, and that is huge. And this could be for each kitchen in India. So that's why this was the motivation for we come up. So this is the simpler version of this unit in which you could see the traditional components, compressors fixed with gas cooler. With gas cooler, we could consider it as a heat reclaim. We are going to generate hot water. We are going to use this heat to generate hot water up to 90 degrees C. Then to increase the overall efficiency of the system, we have implemented multi-ejector units, and there will be two different temperature ranges, medium temperature and low temperature evaporators. And with the support of that, we are going to have cold water to handle the air conditioning side of the unit. And the major important part of this is we are going to implement thermal storages on both sides, hot thermal storage tanks and cold water thermal storage tanks. The purpose of this is to handle the peak load hours. And whenever the system requires uh, hot water, it, it should be there. So to creating to reduce the vibration or changing frequency in the system, these hot thermal storages will be a great beneficial part. So this is how the system would look like once it will be on the ground. So I believe it is not working now. Yes, so this is the real scenario right now. This is the position of the unit. So we have installed all the major components which are required in the system along with the controller pads and other stuff. Only part which is now remaining is the some information from the Danfoss controllers with which the final system controllers will be identified and fixed to run the unit. And once the system will be equipped with all the components and sensors, it will be tested in IIT Madras and will be exported to Bangalore for the real kitchen. So this is the first demo site which we will be having. Second one is which we are progressing now is towards the Goa. So for Goa as a hotel application, you could easily that we are going to provide hot water as well as cold water. Hot water for kitchen, for laundry conditions, and for bathing. And cold water is for air conditioning. So this looks like a bit complex, but bear with me. So let me try to explain this system. It's nothing, but we are going to design two gas coolers after the compressor, as you may need to have different temperature level of water which are required in the hotel. So by keeping that in mind, we are going to design two separate gas coolers for the unit. And definitely the system will be having a ejector with different slots to manage different capacities and different loads. The similar way, system will be having two evaporators. One would be the gravitational bed and other one is taken care by the expansion valve. So the system is simple, but the controlling part is the major element of the section. And for that, on the hotter side, we are going to install 5,000 liter hot water tank, which will be keep on storing the hot water from the unit. And once the system will be having enough water at the required temperature, it will be supplied to the hotel premises, to kitchen or to building. And on the other side, we are going to generate cold water, which will be distributed in the ducting part in the hotel, in the rooms, in the lobby, in the reception area, which will create the air conditioning system. So for that, we are going to have fresh water. And now there's a discussion going on as at the Goa site, the water pH level is high. So to reduce that one, there's another challenge that maybe we are going to have a softener plant or something like that. So that is an ongoing discussion which we are having. But to handle different type of loads, because during the morning hours or maybe in the evening hours, you might require the large quantity of hot water. So the production needs to be according to that. So this storage tanks will handle the change in frequency, as well as you might have seen some areas have different tariff and other situations with which it is easy to handle the system load in the night and could be used this water which will be available in the morning. So this is how we are strategically making it. And the return water which will be available from the hotel premises will be reheated, not it will be directly going towards the mixing with the fresh water, but it is reheating with already water which we have hot water and going back to the system. So this is the effective way of using, and this is how we are designing the controlling strategy of the unit. Second demo site of the hotel is in Chennai now, and we have Koshima as one of our manufacturers. Sorry, for this hotel site, we have research, and for that we are proposing a cascade system, and you might have already know what the cascade system is. In the cascade system, you are going to have two systems in parallel, which will be combined with a cascade heat exchanger. So condenser of one system will be evaporator for the other one, and we are planning to have CO2 on the low temperature side and ammonia on the higher temperature side. And for this system, we are already in talking with the Bell Foods, which are going to design the CO2 side, and they already have expertise in the ammonia side to handle this one. So we are going to handle only and we are going to design the CO2 side, and CIFT is doing that. And same way, we are proposing a number of different compressors. It's pivoting kind of thing. The compressor will work according to the requirement in the load and the capacity of the unit. So this will stay in parallel. The system will have a common heat exchanger known as cascade heat exchanger. Then there will be a IHX, liquid receiver, and there will be a tank in which CO2 will keep the cold CO2 will be keep as a storage, and this will be keep on circulating through the evaporator coil. So we are still discussing which the design of this, how the section would look like, and this will keep on circulating with with the support of the CO2 available, which will be generated through the unit. So this will be the design for our marine demo site. And for the supermarket demo site, we need to have empty and air conditioning unit. So for this demo site, we have proposed one medium temperature evaporator, one low temperature evaporators, along with low temperature compressors, intercoolers, and high temperature compressors, and the gas cooler. As they do not need any hot water so far, so we have designed the gas cooler with air cooled way. So there will be no heat reclaim so far, but the heat extraction through the air cooled gas cooler is designed in a hybrid way. If the temperature would exceed beyond a certain limit, that air that in that condition, it would be difficult to handle this much heat to be extracted through the air cooled. We are going to install one evaporative gas cooler in common to two air cooled gas coolers. So at low load conditions, only air cooled gas cooler will be in operation. But in high load conditions, both air cooled as well as water cooled gas cooler will handle the overall load conditions. So this will all system will also optimize according to that. And there's another design part which we have incorporated. The system will be in a container. It will not be installed in a mechanical room, but it will be holding in a container, and that containers will be kept on the roof of the supermarket to reduce the space area or to optimize the actual size of the system or the location where we need. So only the cooling lines, or you could say liquid lines, or the other return lines will come into this container, and these two containers will be kept on the roof of the supermarket. This is so the action which we are planning to handle all four demo sites which you have already seen. There are different works, civil work, there's the one section, mechanical, electrical, and then this combined make CO2, there will be a series. So first part would be the R&D of the unit, how the system will be manufactured and assembled, how the controller room and cabinets and compound foundation will be discussed in the mechanical room or in the premises, in the hotel or in the supermarket. Where would be the positioning, how the piping and insulation and ducting would be taken care, how the paneling should be neat, the puff paneling, the insulation, another part, how the evaporator will be positioned, the cooling unit will be positioned. Then at the end, how would be the connections, how the strategically connections will happen, the earthing, the lighting, other part. And last part would be the commissioning, how the system will operate and what would be the result. So this is how we are progressing towards the demo site activities. The major part of this project, in which all the demo sites you have already seen the part of the planning and other stuff. The major barriers which we are breaking in this is the awareness barrier. Why we need CO2, why we are discussing about CO2. Knowledge barrier, the things which are not available on the internet but are available only to the person who knows it practically or work with these systems already. Social barriers, we need to discuss the organizational barriers, so legislative. So these are the things which need to be taken care if you want to really have this technology in this system. The outcome, which I would really want to discuss or display, this is the outcome of the unit. Now you could see there are many dots in Indian map in which you could see the upcoming demo sites. There will be one in Goa hotel, one would be in Chennai, then there will be one which are in planning on hospital, and there will be a maritime in Kochi. There will be 4 educational or 5 educational units in the future in India. So there is a lot of information available on ground with experts. One would be in IIT Madras, IIT Bangalore, CFT Kochi, BITS Pilani, IC Kharagpur. Then there are some consultants which are encouraged to work in this field, and there are some vendors. List is big, but I have mentioned only few who already have confirmed they are going to install our system. So this is the progress, and this is the outcome of this project so far within 1.5 years, I would say. So I would definitely, or listening to me, want to encourage that there is a scope. There are many people who just the barriers you need to cross, which we have shown here. These are the barriers which you need to cross to get to know if you're interested. Ask someone, get training. There are some sites which are available. There are some experts which are available in India. This project is there, which could help you to know better about this technology, how this could be work more effectively and more efficiently in the future in the Indian scenario or for different applications. So these all things need to be done by the interesting people. So definitely, I would like to acknowledge my team of this project. So you could see the person from NTNU, the team from Center Ocean, IAR, NEA, CW, IIT Madras, IIC Bangalore, BITS Pilani, and CIFT. And these are our, I would say, next battalion, our postdoctorates and our PhD scholars in this project. So we are really looking forward to explore more opportunities for these new upcoming generation and new students which are recently joined. And also, if someone is interested from the other part of the Indian universities, we would like to have them as well. And thank you for having me and hearing me out. And if you want to contact us, you could have a view on the website which is available, and you will find all the contact information and all the people which are involved in this project. And thank you very much for this. Thank you.
Thank you so much, sir. Participants, if anyone is having any question, please raise your hand. We can unmute you. Any queries from the participants?
Vashak, there is a hand from Mr. Kumar.
You can speak.
Hi, good evening, all.
Yeah.
I have a question. We are talking about this system to implement at bigger scale, as in hotel and some other manufacturing units and colleges. And what is the challenges if we are just putting this system in our household use? And what could be the challenges if we are
Hello.
just putting
Sumit, are you there?
Yeah, Sunil, your voice dropped actually. If you could repeat this.
Okay. My question is, all this system, whatever the demo site we are, the one which you presented, and all are of bigger scale. So my question is, what is the challenges if we are just putting this system in our household use, and what could be the challenge, and can we do it? And that way, I wanted to just have a
No, actually,
your view.
this is the major part of this plan is the system will work if you will have different application, heating as well as cooling. In household, normally have geysers for water heating. We have gases for cooking. We have air conditioning for each room. But if you apply it perfectly, that the hot water which the CO2 unit will produce will be used for bathing, for cooking, for ventilation purpose, and for the cooling side, you are going to use the uh, total generated cooling for the air conditioning as well as for your refrigeration. I believe this is possible, but it needs to be optimized very effectively.
Is there any technical barrier to scale it down the whole system? Like as you have a deep knowledge about it. So if you could answer that.
Well, we are actually targeting on the lower capacity units, but so far we are not, you could say, perfectly scaled that one. But definitely there is a scope. It could be in future there will be system, because in European market the systems are already available, which are scaled down with their technology and with their perfection for the domestic household or for the domestic application. But
Yeah.
definitely it is perfectly possible.
Yeah, but earlier you mentioned like in European countries, they don't have that much of temperature variation throughout the landscape. But here in Indian condition, we can see some part of India has -2 degree, 3 degree, and some part has 48 and 50 degree temperature range. So for that type of system, what we are going to do?
With the same technology, the same system needs to be designed that perfectly. The same components are used in European scenario and in Indian scenario. Only part is their operation will be in subcritical zone, and our challenge is the transcritical, handling the transcritical zone of the system, right? So the
Okay.
challenge is the ambient condition, and if you are going to simulate that conditions very well, then the system is as efficient as it could be used in any part of the globe.
Okay, thank you very much. And we expect more faster. We could see this system in our society. Yeah.
I'm sure we
Yeah.
will. Thank you for
Thank
your
you very
question.
much.
Yeah.
Any other questions from the participants? Participants can type in the chat box also their question. We conclude that there is no further questions from the participants. So, Maya sir, do you want to conclude the section?
Okay, thank you. I thank all the three speakers. Fantastic one. One is Kamath. He gave outline about the control strategies in CO2 systems. Is very important, especially in the CO2 system, because you have to optimize each and every parameter. Pressure, and evaporator flooding, injectors, oil return, everything requires controls. He is a leading person in India, Danfoss, of course, he's a Danfoss person, and he gave an outline only how to control the control strategies. Next, we had Dr. Ramgopal, who is the person who has developed the first transcritical systems in IIT Kharagpur back in early 2000. He did a PhD and happened to be the examiner for the student. I know what the difficulties and how they did the experiment, and they got a good result, and which is comparable to the theoretical results and also the results in elsewhere in the world. He talks in particular about the simultaneous milk chilling as well as pasteurization, which is the one application which can be applied to CO2 refrigeration, because it gives both chilling and heating simultaneously. And in fact, CO2 system is apt for simultaneous heating and cooling. Heating with matching profile. We have got CO2 cools from 100 degrees centigrade to 30 degrees centigrade. We should match that cooling with the heating stream, which is the, in this case, milk. It can be heated. He has talked about many things, including price generation, which is, I think, very dear to Professor Pramod Kumar. He is also doing that power generation from carbon dioxide cycle. So it is very interesting. And lastly, but not the least, Dr. Simarpreet Singh has talked about what we are doing in INDEE project, and what are the prospects of CO2 systems in India, what we are going to, what are the applications in store, how to tackle the problems that may arise, and he gave a brief description about the future of CO2 systems applications in India with demo sites. He has encouraged people to come to IIT Madras and visit demo site systems, which will be in place soon. And this lecture is very encouraging for all of us to see that the systems will come into place very soon. I thank all the three speakers, great speakers, which are wonderful and informative and knowledge sharing. Thank you all, and I thank all the listeners. Still, I got 130 in the. That's I think 200 plus now has come to 130. Even in the late evening, people are listening, and thank you very much. And we will be posting all the recorded messages, like recorded lectures, maybe in one of the sites, so that people can follow it up at any time. So good evening and good night. Thank you all. Have a wonderful part the day left. You can watch the TVs and enjoy and relax. Thank you very much. Thank you all. My panelists also, my co-panelists also, thank you very much for remaining in the show all along. Thank you very much.
Thank you.
Thank you.
Thank
Bye.
you. Thank you, sir.